Welcome to the Whispering Scientist, a quiet corner of the internet where curiosity and calm live side by side. If you are settling in for the night, make yourself comfortable. Let the noise of the day fade away and allow your thoughts to drift through the quiet rhythm of science told slowly. Tonight, we're exploring one of the universe's most mysterious and beautiful ideas, quantum energy. It's the energy that hums beneath everything, from the faint glow of a star to the still air between atoms. You can't see it, you can't hold it, and yet it moves the cosmos. So, close your eyes if you like, breathe deeply, and let's begin our quiet descent into the smallest energy of all. What if even the emptiest space is never truly empty? Energy. We talk about it every day, yet few of us stop to ask what it truly is. It heats our homes, drives our machines, and glows within every star. But when we peer deep enough beneath matter, beneath atoms, energy begins to blur into something stranger, something quantized. The word quantum simply means a discrete amount, a tiny packet of something that can't be divided further. At the dawn of the 20th century, scientists discovered that energy doesn't flow smoothly like water. It arrives in steps, tiny bursts, each one an indivisible spark of reality. This was the beginning of quantum physics, the study of a world so small that the rules of logic start to bend. In this hidden realm, light behaves as both wave and particle, matter dissolves into vibrations, and what we call nothing, the empty space between things, turns out to be alive with invisible motion. It's a universe that never rests, a restless ocean of fields and fluctuations that form everything we see. Over the course of this journey, we'll wander from the first moments of quantum discovery to the vast silence of space itself. We'll meet the scientists who uncovered the strange and sometimes reluctant truths of energy. We'll trace the story of how the smallest quanta of light gave birth to matter, to stars, and ultimately to us. But most of all, we'll learn that energy isn't a thing to be found. It's a rhythm that all of existence dances to. It changes itself, written into the fabric of the cosmos. So as you lie there, letting your thoughts float like dust in a beam of light, consider this. If everything in the universe is made from energy, and even emptiness hums with it, then where does energy itself come from? In the late 19th century, science felt almost complete. The great physicists of the day spoke of their discipline as though it were a grand house already built, with only a few small cracks left to plaster over. Gravity, motion, and electricity were all neatly described by the elegant mathematics of Newton and Maxwell. The world seemed to follow smooth, predictable rules. Yet, hidden in the glow of something as ordinary as a hot piece of metal, there was a mystery that stubbornly refused to behave. When scientists heated objects and measured the light they gave off, the results made no sense. They called these glowing objects black bodies, not because they were dark, but because they absorbed all light that fell upon them. When heated, they shone in beautiful gradients of color, dull red, orange, yellow, white, but when physicists tried to calculate exactly how much energy these objects emitted at different wavelengths, the numbers exploded into nonsense. Classical theory predicted that as the wavelength of light grew shorter, as it reached toward the ultraviolet part of the spectrum, the amount of radiation should increase without limit. If that were true, even a small warm object should shine with infinite energy, a catastrophe in every sense of the word. This absurd theoretical result became known somewhat dramatically as the ultraviolet catastrophe. Enter Max Planck, a quiet, precise German physicist with a fondness for order. He was not the type to chase cosmic mysteries. He preferred neat mathematics and tidy answers. In the year 1900, Planck was trying to make sense of this black body puzzle. Perhaps, he thought, there was some small correction to the formulas, some missing factor that could smooth out the chaos. But when he adjusted his equations, no gentle fix appeared. To make the numbers fit the experimental data, to stop the predicted explosion of infinite energy, he was forced to make a bold and strange assumption. The energy of light was not continuous, it came in discrete chunks. This was a shocking idea. For centuries, scientists had imagined energy as a smooth wave, something that could be divided and subdivided forever. But Planck proposed that energy could only be emitted or absorbed in specific, fixed amounts. He called each chunk a quantum, from the Latin word meaning how much. The size of each quantum depends on light frequency. The higher the frequency, the larger the packet of energy. Planck expressed this relationship with a small constant now known as Planck's constant ch, a number so tiny it defines the scale of the subatomic world. You could think of it as the universe's smallest coin, the minimum currency of energy exchange. For a scientist devoted to classical order, this solution must have felt like a reluctant confession. He later admitted that he had made the leap out of pure desperation, never imagining it would lead to a new physics. Planck was trying to save the existing world of equations, not replace it. But the universe had other plans. When he compared his new formula to the experimental results, it fit perfectly. Every curve of the black body spectrum aligned like notes in harmony. In that quiet triumph, Planck had unknowingly struck the first chord of a new era. What made this so profound was not just the correction of a mathematical error, but what it implied about reality itself. If energy could only come in fixed packets, then nature was not smooth and continuous after all. Beneath the flow of light and heat lay a hidden granularity, a digital texture to existence. It was as if the universe ran not on analog waves, but on cosmic code. Of course, Planck did not see himself as a revolutionary. In lectures, he presented his findings modestly, as if embarrassed by their strangeness. Yet, within a few short years, younger scientists would seize upon his idea and carry it far beyond what he ever intended. His reluctant hypothesis would ignite the deepest transformation in physics since Newton. Planck's discovery was also a reminder of how science often progresses, not through certainty but through discomfort. He wanted tidy numbers, not a revolution, but the data refused to yield until he surrendered to something radical. Sometimes the smallest step taken reluctantly can open a door no one expected to find. To imagine the scale of what he uncovered, picture this. If you took all the energy emitted by a warm object and divided it into the tiniest possible pieces, each one would carry an amount of energy proportional to pleasure. These packets are unimaginably tiny, yet every beam of light that has ever shone, from a candle flame to a galaxy, is made of them. The idea that energy came in quanta was so alien that many scientists resisted it for years, but quietly, it worked. Every experiment agreed. Slowly, grudgingly, the physics community began to accept that Planck's strange little constant was real, and that the universe, beneath its smooth appearance, ticked to an invisible rhythm. There is something almost poetic about it. The smallest possible action, the faintest whisper of energy, defining everything that happens in the cosmos. A single number linking the warmth of a hearth to the steady glow of the distant stars. Max Planck once said that new ideas in science don't triumph because old scientists suddenly agree with them, but because new scientists grow up familiar with them. He was right. His reluctant leap reshaped the world whether he wanted it to or not. From that first spark, that desperate attempt to fix an equation, the quantum age began. And with it, a deeper understanding of energy, not as a smooth wave of motion, but as the universe's smallest, most perfect heartbeat. Years before the 20th century began, the world of physics seemed almost serenely complete. The great scientific minds of the era believed they had successfully mapped the fundamental rules governing the universe. They had elegant, working theories for gravity, for the motion of objects, and for the mysterious nature of electricity and magnetism. The complex, dynamic world seemed to follow the clean, predictable mathematics set down by giants like Isaac Newton and James Clerk Maxwell. The universe, in this view, was like a magnificent, perfectly wound clockwork mechanism, running smoothly and continuously without surprises, yet hidden within a phenomenon as seemingly simple as the glow of a warm object. A quiet alarm was sounding, a mystery that stubbornly refused to fit the established, comfortable rules. The problem focused on what physicists called black bodies. This name did not mean the objects were literally black. It was a technical term for an idealized surface that absorbs all light that falls upon it, reflecting none. When such a body is heated, it glows, emitting light across a spectrum of colors. Think of a piece of iron being heated by a blacksmith. It starts with a dull, barely visible red, progresses to a glowing orange, then to a brilliant yellow, and finally, at the highest temperatures, to a searing white or blue-white. Scientists sought to understand and predict the exact intensity and wavelength of this emitted light based on the object's temperature. They aimed to draw a perfect curve that showed how much energy was radiated at each color. However, when physicists applied the powerful equations of classical physics, the laws of thermodynamics and electromagnetism, to this simple glowing object, the resulting curve matched the experimental data perfectly for the longer wavelengths of light, such as red and infrared. But as the calculations moved toward the shorter, higher frequency wavelengths, like blue and ultraviolet light, the theoretical predictions broke down completely. According to mathematics, the amount of energy emitted by the object should increase without limit as the wavelength becomes shorter. The predicted curve soared endlessly upward, suggesting that even a small, warm object, like a simple iron stove, should instantly radiate an infinite amount of energy, most of it in the high-frequency invisible ultraviolet range. This absurd conclusion became known as the ultraviolet catastrophe. It was a theoretical disaster. If classical physics was truly complete, then this impossible prediction meant either that the universe was governed by nonsense or, more likely, that a fundamental deep piece of the physics was missing. The equations that worked perfectly for explaining the flight of a cannonball or the flow of electricity failed catastrophically when applied to the simple phenomenon of heat radiation. The physics of the time, the grand completed house, had a glaring, fatal flaw, and the ultraviolet light was shining a harsh light on it. Into this intellectual crisis stepped Max Planck, a German scientist deeply dedicated to the classical deterministic view of the universe. Planck was not looking to overturn physics. He wanted to perform a small surgical repair. His aim was simply to find a mathematically sound formula that could accurately describe the radiation curve of the black body from beginning to end, avoiding the infinite energy prediction. He initially hoped to find a correction or an added term that would gently smooth out the chaotic upward spike predicted by the old theories. For months, Planck struggled with the problem, using every tool the classical world offered. No gentle fix appeared. To make the numbers align perfectly with the empirical data, to make his formula match the physical reality of the glowing object, he was eventually forced to introduce a radically new concept. He had to assume that the energy of the radiating body was not being emitted or absorbed continuously as a smooth, unbroken wave. Instead, he proposed that energy could only be transferred in small, discrete, and indivisible packets. This was a profound, shocking leap. Planck suggested that energy was quantized. It was not like a continuous stream of water that could be measured out in any amount, no matter how small. It was like a handful of tiny coins where transactions could only occur in integer multiples of the coin's value. He called each smallest unit of this energy a quantum. The amount of energy E contained in each quantum was directly proportional to the frequency, nu, of the light being emitted. He formalized this relationship with a constant that bore his name, Planck's constant, E equal to hn. The constant is an incredibly small number, but it is one of the most important numbers in the universe. It sets the scale for the tiny granular world of subatomic physics. It acts as a fundamental limit, telling the universe the smallest possible amount by which energy can change or be exchanged. For a man who valued certainty, Planck's idea felt like a desperate measure. He introduced the quantum hypothesis reluctantly, viewing it initially as a mathematical trick, a tool to make the formulas work, rather than a deep truth about the nature of reality. He spent years trying to reconcile his quantum idea with the old continuous classical physics, never fully comfortable with the strangeness he had unearthed. He wanted to save the old house, but in plastering the ultraviolet crack, he had introduced a completely new foundation. When Planck's formula, built on this radical assumption of quantized energy, was tested against the experimental data for the black body, it worked perfectly across the entire spectrum, from the longest infrared waves to the highest ultraviolet frequencies. It elegantly solved the ultraviolet catastrophe, not by making a correction, but by replacing the old smooth view of energy with a new granular one. The infinite energy predicted by classical physics simply could not happen because energy could not flow in the infinitesimal amounts required by the short wavelengths. It could only move in definite, fixed packages defined by h. This quiet triumph was the true dawn of quantum physics. What Planck had revealed was that reality itself has a hidden digital texture. The universe, beneath its smooth appearance, ticks to a secret rhythm, exchanging energy in discrete packets. This was a direct, fundamental contradiction of the long-held classical belief that nature was smooth and perfectly continuous. To grasp the scale of this change, imagine the comforting touch of a warm object. That warmth is energy radiating outwards. Before Planck, you would assume that radiation was a smooth, endless outward flow. After Planck, you realized that the warmth is actually a hail of invisible tiny bullets, each carrying a precise, indivisible quantity of energy. They travel together for countless distances, yet each one is minted with an exact value determined by its frequency. Planck's legacy is profound. His reluctance to embrace the revolutionary implications of his own discovery is a poetic reminder of how science often advances by the uncomfortable necessity of data demanding a new idea. He wanted order, but the universe forced him to invent the concept of the quantum, the smallest possible action, the faintest whisper of energy that paradoxically defines everything that happens in the cosmos. His small constant became the universal language that links the mundane glow of a warm object to the furious fire of a star, changing forever how we understand light, heat, and the very composition of reality. From that quiet, desperate mathematical fix, the quantum revolution truly began. A few years after Max Planck's reluctant discovery that energy was quantized, a young, quiet patent clerk in Switzerland was thinking about light. His name was Albert Einstein. At the time, he was only 26 years old, working long hours examining inventions for the patent office in Bern and spending his evenings wrestling with the subtle riddles of physics that no one else seemed to be noticing. In the year 1905, a year now remembered as his annus mirabilis, or miracle year, he published a series of papers that would forever change how we see the universe. One of those papers tackled a puzzle so ordinary it almost seemed unworthy of his genius. Why does shining light on certain metals cause them to release tiny sparks of electricity? This phenomenon was called the photoelectric effect. Physicists had already observed that when ultraviolet light was directed at a metal surface, electrons were ejected, creating a measurable electric current. But the details of this process were strange and deeply confusing to the classical worldview. Brighter light didn't necessarily knock out more energetic electrons. Instead, only light above a certain color, or, more precisely, above a certain frequency, could dislodge them at all. No matter how intense a beam of red light was, no matter how long you shone it, it simply did nothing. Yet, a faint beam of blue or ultraviolet light could cause an instant spark and a current to flow. Classical physics couldn't explain this selective behavior. According to the wave theory of light, increasing the brightness should increase the total energy delivered to the electrons, making them fly off faster. It didn't. Electrons seemed to be ignoring the brightness of the light and only responding to its color or frequency. The total energy hitting the metal didn't matter. Only the quality of the light did. Einstein, reading Planck's revolutionary work carefully, took a daring conceptual step. What if Planck's strange idea, that energy came in discrete packets, applied not just to how matter emitted light, but to light itself? What if light wasn't just a smooth wave, but a collection of energy quanta, tiny indivisible particles of pure energy? He called these particles light quanta. Today, we know them as photons. Einstein proposed that each photon carried an amount of energy proportional to its frequency equal to h nu, borrowing Planck's constant h. The higher the frequency, the higher the energy of the individual photon. Blue and ultraviolet light have shorter wavelengths and higher frequencies, meaning they carry significantly more energy per photon. Red light has longer wavelengths and less energetic photons. When a photon strikes the surface of a metal, it behaves like a miniature, invisible bullet. It can knock out an electron, only if it carries enough energy to overcome the electron's binding energy, the gentle force holding it to the atom. A bright red light may throw countless photons at the surface, but if each one lacks the required punch, the necessary minimum quantum of energy, none will succeed in freeing an electron. A single high-frequency ultraviolet photon, however, carries more than enough energy to do the job instantly. This explanation was revolutionary because it shattered the comfortable certainty that light was purely a wave. For centuries, experiments had confirmed light's wave-like behavior. It could bend, interfere, and diffract. But Einstein's paper suggested something radical. Light was simultaneously a wave and a particle. Depending on how you looked at it, light could ripple like water or strike like a hail of invisible bullets. This paradox, the wave-particle duality, would haunt and inspire physicists for the rest of the century. Einstein's proposal was bold, and not everyone welcomed it. Even Planck himself hesitated to accept the idea that light, which he considered a smooth field phenomenon, was made of discrete particles. Yet, experiments kept confirming Einstein's prediction. The energy of the ejected electrons depended solely on the frequency of the light, exactly as his equations described. The photoelectric effect was not only real, it became one of the most precisely verified phenomena in modern physics. Decades later, this quiet discovery, not his more famous work on relativity, would earn Einstein the Nobel Prize. In everyday life, this strange behavior is around us. Every time sunlight hits a solar panel, photons are absorbed by the atoms in the panel's surface. Their energy knocks electrons loose, creating an electrical current. This is the exact principle Einstein described in 1905. The light shining on your phone's camera sensor, the glow of an LED light, and even the operation of automatic doors that use photosensors all rely on the subtle, constant transaction of the photoelectric effect. The universe, it seems, is built on this quiet, rhythmic exchange, photons trading energy with matter coin by coin. Each photon is a tiny packet of currency, a coin of light minted in the furnace of the universe, exchanged across the vast marketplace of reality. This discreteness was more than a clever fix for an experimental problem. It was a profound shift in how scientists understood the world. Classical physics imagined energy as something smooth and continuous, like a flowing river. Einstein showed it could also behave like a shower of pebbles. And yet, light never stopped being a wave, it was somehow both. This profound ambiguity hinted that the universe might be built from information, discrete packets of energy behaving like notes in a cosmic symphony. Imagine a beam of sunlight streaming through a window. To your eyes, it's a single continuous ray, but in truth, it's an orchestra of photons, each one vibrating at its own frequency, each carrying a precise quantum of energy across the vast emptiness of space. They travel together for millions of years, only to end their journey by striking your skin, warming it by the smallest imaginable degree. That warmth, the comforting touch of sunlight, is the sum of countless tiny collisions, each photon giving up its precise energy to your atoms. Einstein's light quanta forced science to accept that nature is more mysterious than intuition suggests. It blurred the boundaries between energy and matter, between waves and particles, between the seen and the unseen. And perhaps most intriguingly, it hinted that the universe doesn't owe us simplicity, it only asks us to pay attention to the evidence. A century later, the photoelectric effect still powers much of our modern world. Yet it also reminds us that even the most familiar things, like the light pouring through your window, are woven from mysteries deeper than imagination. Light, after all, is not just illumination, it is the universe communicating through energy, one photon at a time, each carrying its precise quantum of energy, unbroken and unchanged since the moment it was born. From a small mystery involving a bit of metal and a beam of light, Einstein made the invisible tangible. He turned Planck's abstract quanta into something that could be measured, tested, and felt. He showed that light itself is continuous and discrete, elegant and strange. After Einstein showed that light itself comes in tiny packets of energy, the photons, the next profound question that gripped the scientific community was what this meant for matter. If light was quantized, could the invisible structure of atoms be too? In the early years of the 20th century, atoms remained mysterious, tiny, invisible structures that seemed to defy the simple, predictable explanations of classical physics. Scientists knew that atoms contained negatively charged electrons and a positive central nucleus, but no one could truly understand two critical facts. First, why did atoms give off light only in such precise colors? And second, why didn't the electrons simply spiral into the center, like miniature planets falling into a sun, causing all matter to instantly collapse? It was a brilliant and endlessly curious Danish physicist named Niels Bohr who found a clue, and he did it by carefully listening to what he called the music of the atom. In 1913, while working in England, Bohr began to reimagine the structure of the atom, taking the new quantum ideas that Planck and Einstein had revealed and applying them directly to the particles of matter. Bohr proposed something radical that married the stability of matter to the new granularity of energy. Electrons could only occupy specific, allowed orbits around the nucleus, each corresponding to a distinct fixed energy level. They couldn't exist in between these levels any more than you could stand halfway up a staircase without a step beneath you. The allowed orbits were like precise, mathematically defined rungs on an energy ladder. In Bohr's picture, an electron moving in its allowed orbit was perfectly stable. It would not continuously lose energy or crash into the nucleus, as classical physics demanded. The collapse of the atom was impossible because the lowest, innermost orbit was the electron's ground state. It could not fall any lower without violating the absolute, non-negotiable rules of quantization. In effect, the universe had built safety rails, quantum constraints, into the structure of the atom itself, guaranteeing its enduring stability. The crucial part of Bohr's theory explained the mystery of light emission. An atom only emits or absorbs a photon, a packet of light energy, when an electron jumps from one allowed orbit to another. When an electron leaps from a higher energy level down to a lower one, it must release the energy difference between the two steps. That released energy takes the form of a photon, and the energy of that photon, according to Planck and Einstein, determines its precise frequency or color. Conversely, an atom absorbs a photon only when that photon carries the exact, specific amount of energy needed to kick an electron up from a lower level to a higher one. This simple, elegant idea explained at last why atoms emitted light in such sharply defined colors. If you pass the light from a glowing gas through a prism, it doesn't form a continuous, smooth rainbow. Instead, it forms a set of thin, bright lines, a unique barcode of color known as an emission spectrum. Each chemical element has its own signature pattern of lines. Hydrogen, for example, produces distinct lines in the red, blue-green, and violet regions. These lines had puzzled scientists for decades, but Bohr's model suddenly made sense. Each specific line represented a specific, allowed energy jump made by an electron within the atom. Every atom, Bohr suggested, had its own internal ladder of energy levels, and those ladders were different for every element. It was as though every atom played its own tune in a universal orchestra, with each distinct note produced by an electron's leap between fixed levels. The sharp streaks of color you see from burning elements are that atomic music made visible. Bohr's model was simple yet powerful. It worked perfectly for hydrogen, the simplest atom of all, which has only one electron. Later refinements by other scientists would show that the story was more complicated for heavier atoms, where the single orbit picture gave way to complex suborbits. But the core principle remained unshakable. Energy levels were quantized, and electrons could only occupy those discrete spaces. Nature, it seemed, preferred order and mathematical harmony to chaos. Bohr's idea might sound abstract, but its fingerprints are everywhere in our sensory world. The very colors we see every day, the red of a sunset, the blue of the sky, the green of a leaf, all depend on which photons are absorbed or emitted by atoms and molecules based on their quantized energy levels. When an atom absorbs a photon, one of its electrons jumps up to a higher level. When it releases a photon, the electron falls back down, releasing light of a specific, predictable wavelength. You see this most clearly in the soft, steady glow of a neon sign. When electricity passes through the gas inside the tube, it energizes the neon atoms, exciting electrons to higher orbits. As those electrons instantly return to their original stable energy states, they emit light of a particular reddish-orange color. Change the gas to argon, helium, or krypton, and you get new, distinct colors, each one the signature of that element's unique quantum structure. Every glowing sign is a public display of atomic precision, a quiet concert of electrons leaping between fixed notes. The same principle explains the colors of stars. When astronomers look at the light from a distant sun and pass it through a spectroscope, they see lines missing from the spectrum, dark bands where certain precise wavelengths have been absorbed by the elements in the star's atmosphere. These dark lines act like fingerprints, allowing scientists to determine what the star is made of without ever visiting it. We can identify hydrogen, helium, sodium, iron, and even trace amounts of rare elements. All this is possible because electrons obey Bohr's quantized rules. This is the astonishing power of Bohr's idea. It connects the smallest scales of matter to the largest scales of the cosmos. The same quantum jumps that produce the color of a candle flame also mark the light from galaxies millions of light years away. The laws that govern an atom in your skin are the same ones that govern the birth and death of distant stars. And yet, for all its revolutionary elegance, Bohr's model was still simplistic. In reality, electrons don't orbit the nucleus like planets on a single path. They exist as standing waves spread out like clouds of probability. But Bohr's insight was still a monumental step. It gave scientists a language for describing atomic behavior that matched experiments with breathtaking precision. It also gave the world a new kind of aesthetic. The idea that atoms had allowed states and forbidden zones suggested a deep harmony in nature. Electrons couldn't improvise or wander freely, they could only leap between the notes written into their structure. Electrons do not improvise. They perform precise, beautiful solos. The atoms that make up your body are playing too, their electrons forever shifting and humming, releasing tiny internal flashes of light too faint to see. If you could somehow hear them, the entire cosmos would sound like a symphony of vibration and exchange, a billion instruments playing in perfect mathematical time. And all of that began with the simple, profound idea that electrons are not free to go wherever they please, but must step carefully between their allowed precise energies. From the first spark of Planck's quantum to the structure of atoms themselves, the universe revealed that its foundation is made not of continuous matter or smooth motion, but of patterns, energy arranged in steps, like notes on a cosmic scale. Every atom hums a melody, and light is its quiet song. By the early 1920s, the picture of the atom was beautifully structured but still incomplete. Niels Bohr's tidy orbits worked wonderfully for the simplest atom, hydrogen, giving a precise, musical explanation for its spectrum of light. Yet, when scientists tried to apply the same model to more complicated atoms, the neat mathematics began to fall apart. Electrons were not behaving quite like miniature planets after all. They seemed to exist in ways that defied exact location, appearing both here and there, moving and yet not moving all at once. The classical image of an orbiting particle, elegant as it was, simply couldn't capture their true, subtle nature. Something deeper was needed, a way of describing matter that embraced its inherent strangeness instead of trying to force it into old, familiar patterns. In 1926, an Austrian physicist named Erwin Schrödinger began to think differently. He had been fascinated by waves since childhood, by how vibrations on a taut string could form standing patterns of sound, holding their shape while vibrating. The groundbreaking idea that matter itself might behave like a wave had been proposed earlier by Louis de Broglie, a French prince turned physicist, who suggested that every particle, from an electron to a cannonball, has a wavelength related to its momentum. It was a bold concept, suggesting that perhaps electrons didn't orbit the nucleus like tiny marbles, but flowed around it like ripples around a quiet stone. Schrödinger decided to take that wave idea seriously and to write down the fundamental mathematics that could precisely describe it. The result became known as the Schrödinger equation, a deceptively simple formula that would change physics forever. Instead of describing electrons as points in space, Schrödinger described them as wave functions, psi, patterns of probability that spread through space like soft, vibrating fog. The wave function didn't tell you exactly where the electron was, it told you where it was likely to be. Its peaks represented high probabilities of location, and its troughs, low ones. This hazy cloud of potential was astonishing. The act of measurement, observing or interacting with the electron, would cause this cloud of possibility to momentarily collapse, revealing one concrete outcome from the many possibilities inherent in the wave. The atom, in this view, was no longer a predictable clockwork system of moving parts, but a shimmering blur of probabilities. Within it, energy and matter merged into one seamless, elegant dance of chance and structure. Where Bohr's atom had sharp, definite orbits, Schrödinger's atom had standing waves, continuous and elegant patterns of vibration that wrapped perfectly around the nucleus. The allowed energy levels of the atom, which Bohr had simply assumed were allowed, now corresponded to wave patterns that fit neatly without overlap or interruption. Just as a guitar string can only vibrate at certain whole number frequencies, harmonics, to produce a clear note, electrons could only exist in wave forms that resonated perfectly with the space around the nucleus. This picture explained with profound insight why electrons could only occupy discrete energy levels. If a wave pattern didn't fit, it simply couldn't exist as a stable state. Energy quantization wasn't an arbitrary rule, it was the geometry of the wave itself. Bohr had described the result, the fixed energy steps. Schrödinger showed the underlying reason, the necessary resonance. The beauty of this model lay not only in its accuracy, but also in its imagery. If we could somehow see the atom as Schrödinger did, we wouldn't find little dots circling a nucleus. We would see shapes, vast, ghostly clouds with varying densities, each representing the probability of finding an electron in that region. The simplest hydrogen atom would appear as a soft sphere of mist, fading gradually into space. Higher energy atoms would form more complex patterns, dumbbell shapes, clover leaves, toroidal rings, intricate geometries of possibility that look almost like abstract art. These probability clouds are not static, they shimmer, shift, and merge as electrons move between states. Yet, the movement isn't mechanical, it's statistical. The atom's entire architecture is defined by probability itself. The idea that something so concrete, the matter that makes up your body, your desk, and the world around you, could be built upon uncertainty, was both thrilling and deeply unsettling. For many physicists, including Schrödinger himself, this probabilistic nature of reality was difficult to accept. He once joked that he did not like the concept of jumping electrons or randomness in fundamental laws, but the experiments proved him right. Wherever scientists looked, they found that the mathematics of wave functions predicted nature's behavior with breathtaking precision. It is strange to think that the universe is built not from certainty, but from possibilities weighted by likelihood. Yet, paradoxically, this surrender of precision gave physics more predictive power than ever. With Schrödinger's equation, scientists could predict how atoms bind together to form molecules, how materials conduct electricity, and even how stars fuse elements in their cores. Chemistry itself became an expression of wave patterns, an art of probability sculpted by energy. If you pause to picture this world, it's hauntingly beautiful. Imagine every atom around you, in the air, in the fabric, in your own skin, as a network of shimmering clouds. Each one is buzzing with silent potential. The space that seems empty between the nucleus and the electron isn't truly empty, it's filled with the hum of mathematical possibility. Those electron clouds overlap and blend, forming the bonds that hold everything together. You are quite literally made of probabilities that have, for the moment, chosen to exist in a stable configuration. In this way, the atom becomes a kind of cosmic instrument. Each allowed wave pattern corresponds to a particular energy level, a distinct note in the atom's song. When an electron transitions from one pattern to another, it emits or absorbs a photon, a musical tone of light whose frequency matches the difference between the two notes. The colors of the world, the glow of stars, and the shimmer of metals all emerge from this grand resonance of waves and quanta. Schrödinger's theory also carried a quiet philosophical weight. It suggested that nature doesn't draw hard, deterministic lines between things. Instead, it trades certainty for elegance. Instead of saying where something is, it gives us a rich landscape of where it could be. Reality at its core is fluid, not a series of static objects, but a continuous vibration of information and potential. This realization changed more than physics. It reshaped how humans think about existence itself. The universe doesn't ask for approval, it simply is. The dice roll, whether we watch or not, and curiously, the randomness is not chaotic, but ordered, following strict statistical laws that make the unpredictable, in a profound sense, predictable after all. Today, the shapes predicted by Schrödinger's mathematics can be visualized with computers, revealing a hidden architecture beneath everything we see. These visualizations show astonishingly intricate layers of symmetry and geometry that rival the patterns in snowflakes or seashells. Every orbital shape, every subtle fold of probability, is a product of energy finding the most harmonious, resonant way to exist. When you look around and perceive the solidity of the world, it's easy to forget that it's all built on uncertainty. Yet this fundamental uncertainty is precisely what allows atoms to form bonds, molecules to flex and twist, and life to adapt and thrive. A perfectly rigid, deterministic universe would be sterile. It's the tiny flicker of chance, the wave of potential beneath every particle, that makes the universe alive with creativity. So the next time you picture an atom, don't imagine small spheres whirling around a nucleus. Instead, imagine music frozen in space, standing waves of energy resonating in harmony. Within each vibration lies the possibility of light, of matter, of everything we know. And perhaps that is the most elegant truth of all, that existence is not a thing, but a melody, a quantum wave endlessly resonating, shaping the patterns of reality, beautiful, uncertain, and profoundly alive. In the strange and intricate world of the quantum, even the act of simply looking can profoundly change what you find. This isn't just poetic language, but one of the most fundamental and unsettling discoveries in all of science. By the mid-1920s, the atom was understood to be built from wave functions and probabilities. But a young German physicist named Werner Heisenberg stumbled upon a truth that placed a fundamental, unavoidable limit on human knowledge. This truth was so contrary to classical intuition that even Einstein found it difficult to accept. Heisenberg showed that nature places a fundamental limit on what can be known simultaneously about a quantum particle. The sharper you try to measure one property of a particle, the blurrier another related property becomes. This is the uncertainty principle, though that word uncertainty doesn't quite do it justice, as it implies a lack of certainty that is temporary. This is not about human error or clumsy or imperfect instruments. It's about the fabric of reality itself. Even in a perfect, theoretically flawless experiment, no amount of cleverness can break this rule. If you try to measure an electron's exact position, you fundamentally lose track of its momentum, its speed and direction. Pin it down and its movement becomes instantly unknowable. Watch how fast it moves, and its location blurs into a smear of possibility. It is as if nature insists that precision in one area must always be paid for with a necessary, irreducible mystery in the other. Heisenberg's idea was profoundly revolutionary. Until then, physicists assumed that if they could only build better, more precise tools, they could eventually know everything about a physical system, exactly where every particle was, and precisely how it moved. But the quantum world refused to cooperate. At these tiny, fundamental scales, measurement itself becomes part of the story. To see an electron, you must shine light, a photon, on it. But the very act of the photon striking the electron to observe it also imparts energy, instantly nudging the electron out of place. There is no way to peek without poking. Observation and disturbance are inseparable. The principle can be written in a single line of elegant mathematics, but its meaning is far deeper than a formula. It tells us that reality is not a static picture waiting to be examined. It is an active, restless dance. Every particle jitters with an intrinsic uncertainty, as though reality itself trembles too fast for absolute stillness. That inherent jitter, though invisible to us, is the fundamental engine of everything that happens. To understand how profound this is, imagine a violin string vibrating gently in the dark. The exact position of the string at any single moment can never be pinned down precisely. It's constantly moving through a range of possibilities. That vibration is the music. Without that motion, there would be silence. In the same way, the universe's inability to stay perfectly still is what gives rise to energy itself. The tremble of uncertainty is what keeps existence alive. Heisenberg's uncertainty also applies critically to time and energy. You cannot know both with perfect accuracy. The shorter the duration you examine, the less precisely energy can be defined. This is not a flaw, it's a kind of permission slip written into the laws of physics. For incredibly brief moments, energy can fluctuate, appearing or vanishing like sparks in darkness, as long as it balances out in the end. Nature allows these tiny temporary loans of energy, provided they are repaid almost instantly. These momentary fluctuations are not just theoretical concepts, they happen everywhere, constantly, even in what we call empty space. This gives rise to virtual particles, tiny flashes of matter and antimatter that flicker into and out of existence, borrowing energy from nothingness and then returning it before anyone can catch them. They live for unimaginably short times, perhaps trillionths of a trillionth of a second, yet their presence leaves a measurable imprint. The mysterious attraction between two uncharged metal plates in a vacuum, known as the Casimir effect, arises directly from this restless sea of temporary particles. The vacuum, it turns out, is never truly empty. It is an ocean of potential energy and perpetual invisible motion. When you think about it, this restlessness is strangely comforting. The universe is not static or mechanical, but alive with activity. Even in its quietest moments, stillness in the absolute sense doesn't exist. Everything vibrates, everything fluctuates. Even the atoms in your body tremble with quantum uncertainty, their electrons forming shifting clouds of probability. This blurring between what can and cannot be known also forces us to rethink what it means to truly understand something. For centuries, science sought to describe the world in perfect detail, to measure, predict, and control. Heisenberg's discovery gently reminds us that total, microscopic control is an illusion. The closer you look, the more the world slips through your fingers. But far from being a failure, this uncertainty is a source of freedom. It enables creativity, complexity, and life itself. If particles could be pinned down precisely, if the universe were perfectly predictable, nothing truly new could ever happen. There would be no surprises, no spontaneity, no genuine change. The uncertainty principle ensures that the future is not carved in stone, but carved in mist. It leaves room for the universe to breathe. Einstein, ever the realist, was deeply troubled by this notion, famously remarking that God does not play dice with the universe. But quantum mechanics cheerfully replied that not only does God play dice, the dice are still rolling everywhere all the time. And the astonishing thing is that this cosmic randomness doesn't lead to chaos. It averages out to produce the stable, ordered world we see. From the jittering of electrons comes the solidity of matter. From chance arises a pattern. You could say that the uncertainty principle is the heartbeat of quantum energy. Those tiny fluctuations, the inability of particles to sit perfectly still, are what make phenomena like zero-point energy possible. Even at absolute zero temperature, when all thermal motion has stopped, the uncertainty principle ensures there's still a faint vibration left, a whisper of energy that can never be completely removed. The universe, it seems, refuses to go completely quiet. This is more than an abstract scientific fact, it's a profound philosophical statement. It means that change is built into existence. Nature's smallest building blocks are restless, not because they want to be, but because they must be. Reality doesn't pause. It oscillates, flickers, and hums. Everything we see, every atom and star, is an echo of that foundational tremble. When you sit quietly and feel the pulse of your own heartbeat, that rhythm, that alternation between presence and pause, is mirrored in the very foundations of physics. The universe balances itself, trembling delicately in between. Reality is not solid and still, it's alive with motion, too quick for our eyes to catch. Every atom, every field, every patch of vacuum space participates in this grand uncertainty dance, a waltz of probabilities and possibilities spinning forever in the light of existence. And in that motion, in that shimmering imperfection, lies the most remarkable truth of all. Perfection isn't stillness, it's a movement. The universe doesn't need certainty to be beautiful, only balance. By the time physicists had grown comfortable with electrons behaving like waves of probability, another fundamental question emerged. If particles could behave like ripples, then what precisely was doing the rippling? The idea of matter as both wave and particle was astonishing, but it was only half the story. Beneath the shimmering clouds of probability lay something deeper, something that would redefine what matter and energy even meant. This was the quiet beginning of the quantum field revolution, a conceptual shift so profound that it subtly rewrote the very foundations of reality itself. The clue came from an old familiar friend, the electromagnetic field. Long before the quantum era, scientists had discovered that electric and magnetic forces could be described as invisible fields filling all of space. Move a charged particle, and the field changes, disturb it, and waves of electromagnetic energy ripple outward at the speed of light. These ripples, as Einstein had shown, were what we call light itself, and they were made of photons, each one a tiny packet of energy. When the quantum picture arrived, physicists realized something extraordinary. Those waves weren't abstract phenomena, they were physical excitations of an underlying continuous field. This logic was then expanded. If light came from oscillations in the electromagnetic field, perhaps everything came from similar continuous fields. Every particle, electron, proton, quark, and beyond, might be just a ripple in its own invisible sea. The revolution suggested that instead of tiny, solid particles moving through empty space like billiard balls, reality was an ocean of continuous fields, each capable of producing the ripples we call particles. Imagine the universe as a vast, overlapping collection of invisible oceans. There's the electron field, the photon field, the quark field, and dozens of others, all interwoven and continuous, filling every corner of space. Critically, they're not floating in space, they are space. Empty air, interstellar vacuum, the gap between your hands, all of it is thick with these unseen fields, humming quietly with inherent potential. When one of these fields is excited, as say a tiny pulse of energy travels through the electron field, we detect it as an electron. That's right, an electron isn't a little solid speck, it's a vibration, a localized ripple in an ever-present field that extends across the entire universe. Knock that ripple away, and the field remains, calm and ever ready to vibrate again. It's a radical thought, and yet the mathematics leaves no doubt. Fields are the fundamental ingredients of reality. Particles are the temporary disturbances, the excitations that rise and fade like waves on the surface of a pond. Even a single atom is a collection of synchronized vibrations, a miniature symphony of interacting fields. The photon, the particle of light, is a ripple in the electromagnetic field. The electron, a ripple in the electron field. Quarks, the building blocks of protons and neutrons, are ripples in their respective quark fields. When these fields interact, energy transfers from one to another. A photon interacts with the electron field to create light. A gluon mediates the delicate dance between quarks inside an atomic nucleus. Every physical event, every spark, collision or heartbeat, is an exchange of energy between these invisible seas. In this view, The universe becomes less like a collection of separate objects and more like a grand vibrating fabric. The familiar idea of matter as solid stuff gives way to something far more elegant, patterns of movement. What we perceive as solid and permanent is really the quiet play of fields, waves appearing stable because of their rhythm. This realization turned physics inside out. Instead of asking what the universe is made of, scientists began asking how it behaves. The fundamental question shifted from what is a particle to what does the field look like when it moves. Every experiment in modern particle physics, from the smallest laboratory setup to the colossal collisions inside the Large Hadron Collider, is really a way of poking these fields and watching the ripples they produce. When physicists first detected the Higgs boson, they weren't discovering a new particle so much as confirming the existence of the Higgs field itself, catching one fleeting wave crest in an ocean that had always been there. The event lasted only an instant, but it proved that the sea beneath reality is profoundly real. It's a humbling thought. The solidity of your chair, the light from your lamp, even the atoms in your body are not separate entities floating in emptiness. They're different vibrations of the same universal fabric. You are quite literally a pattern in motion, a fleeting arrangement of ripples in a cosmic sea. In this light, the old philosophical debate about matter versus energy begins to dissolve. They're not two different things at all, but two ways of describing the same underlying phenomenon. Fields are energy structured by rules and symmetries that cause the diversity of the universe. When those fields ripple, we see particles. When they appear to rest, we call it empty space. Still, rest is an illusion. According to quantum theory, a field can never be perfectly still. The uncertainty principle guarantees a faint vibration even in the absence of particles, a baseline hum known as zero-point energy. It's as if the universe cannot endure. Even in perfect darkness, something moves. Quantum field theory, the framework that unites all these ideas, is arguably the most successful theory in science, predicting the behavior of particles to astonishing precision, sometimes to more than 10 decimal places. And yet, it carries a strange serenity, an almost spiritual elegance. It says that the entire universe, from galaxies to atoms, emerges from a single continuous fabric of fields endlessly weaving and unweaving themselves. When you begin to picture the world this way, solidity and emptiness lose their hard meaning. Every surface, every star, every breath is a ripple in something larger, invisible, and profoundly connected. There is no true separation, only patterns interacting across an ocean of potential. Matter, then, is not made of matter. It's made of structure, of rhythm and resonance, of movement in the dark. The universe is less a machine and more a melody played in the silent language of fields. So when you look at your hand or a falling leaf or the distant shimmer of starlight, what you're really seeing is the same thing in countless forms, the quiet, endless motion of invisible oceans overlapping through everything. Matter is not made of things. Matter is made of motion. Matter is not made of stuff, but of patterns moving in the dark, and the very deepest vacuum, the space we once called nothing, is where the whole vibrant spectacle begins. By the time physicists had grown comfortable with electrons as waves of probability, the underlying structure of reality demanded a deeper explanation. Waves ripple, but they must ripple in something. If particles were merely vibrations, then the space they moved through couldn't be a cold, empty stage. It had to be a medium itself, alive with potential. This conceptual leap, the movement from the idea of discrete particles to continuous interacting quantum fields, was the moment the universe revealed its most profound and elegant secret. This revolution suggested that reality, at its most fundamental level, is an ocean of fields, each one infinite, invisible, and alive, with gentle motion. Imagine the universe not as a collection of separate objects floating in a void, but as a vast, overlapping, interwoven collection of seas. There is the electron field, the photon field, the quark field, and dozens of others, all coexisting and continuous, filling every single corner of space. They are not contained by space. They are the fundamental substance of space. Empty air, interstellar vacuum, the gap between your hands, all of it is thick with these unseen fields, humming quietly with potential. When one of these fields is excited, When a tiny discrete packet of energy travels through the electron field, we perceive it as an electron. That's right, an electron isn't a small solid speck with a fixed location. It's a vibration, a localized ripple, a quantum of excitation in a continuous field that stretches across the universe. Knock that ripple away, and the field instantly remains, calm and ever ready to vibrate again. This conceptual framework is one of the most radical thoughts in physics, yet the mathematics behind it, known as quantum field theory, leaves no doubt. Fields are the fundamental ingredients of reality. Particles are the fleeting disturbances, the temporary wave crests that rise and fade on the surface of these invisible seas. Even a single atom, in this view, is a collection of synchronized vibrations, a miniature symphony of interacting fields. The photon, the particle of light, is a ripple in the electromagnetic field. The electron is a ripple in the electron field. Quarks, the building blocks of protons and neutrons, are ripples in their respective quark fields. When these fields interact, energy transfers from one to another. A photon interacts with the electron field to create light. Every physical event, every spark, collision, or heartbeat is a seamless exchange of energy between these invisible seas. In this view, the universe becomes less like a collection of separate hard objects and more like a grand, shimmering, vibrating fabric. The familiar idea of matter as solid stuff gives way to something far more elegant, patterns of movement. What we perceive as solid and permanent is really the quiet play of these fields, waves appearing stable because of their predictable rhythm. Take the relationship between the fields of matter and the fields of force. Fields that give rise to particles, like the electron field, interact through other fields that give rise to forces. The force of electromagnetism, for instance, is mediated by the continuous exchange of photons, ripples in the photon field between charged particles, ripples in the electron field. Every time a magnet pulls metal, every time light travels across a room, you are witnessing the language of fields, a silent, continuous conversation where energy transfers from one sea to another. This realization turned the core questions of physics inside out. Instead of asking, what is the universe made of, scientists began asking, how does the field move? Every experiment in modern particle physics, including the colossal collisions inside accelerators, is designed to poke these fields and watch the ripples they produce. When physicists first detected the Higgs boson, they weren't discovering a new piece of matter so much as confirming the profound existence of the Higgs field itself, catching one fleeting wave crest in a universal ocean that had always been there. The event lasted only an instant, but it proved that the sea beneath reality is profoundly real. The Higgs field itself is a critical part of this cosmic ocean. It permeates all of space, and when certain particles interact with it, they gain mass. This doesn't happen because the field weighs them down, but because it resists their motion in a particular way. Particles that couple strongly with the Higgs field, such as the top quark, acquire immense mass. Particles that barely interact, like electrons, stay light. The photon, however, doesn't interact with the Higgs field at all, which is why light has no mass and can race through the universe at its ultimate speed limit. You might say the Higgs field gives the universe its substance, not by adding matter, but by shaping how particles move through its quiet resistance. Without this field, there would be no atoms, no planets, no people. Everything would zip through the cosmos at the speed of light, never able to slow down or clump together. To visualize all this, close your eyes and imagine the overlapping oceans, each one infinite, invisible, and alive with gentle, patient motion. When they ripple, they give birth to the physical world. Where they intersect, forces arise. Where they stabilize, matter takes form. Even in the vastness of intergalactic space, where no atoms drift and no visible light passes, these fields remain. They cannot be switched off. Space itself is never truly empty. It's the calm surface of a deep and perpetually restless sea. In this light, the old philosophical debate about matter versus energy begins to dissolve. They are not two different things at all, but two different states of the same underlying quantum field. Fields are energy structured by mathematical rules and symmetries that cause the diversity of the universe. When those fields ripple, we see particles. When they appear to rest, we call it empty space. Still, rest is an illusion. According to quantum theory, a field can never be perfectly still. The uncertainty principle guarantees a faint, unavoidable vibration, even in the absence of particles, a baseline hum known as zero-point energy. It's as if the universe cannot bear absolute silence. Even in perfect darkness, something moves. The vacuum, the space we once called nothing, is alive with motion, too fast for our eyes to catch. This framework, quantum field theory, is arguably the most successful theory in science, predicting the behavior of particles to astonishing precision. And yet, it carries a strange serenity, an almost spiritual elegance. It says that the entire universe, from galaxies to atoms, emerges from a single continuous fabric of fields, endlessly weaving and unweaving themselves. When you begin to picture the world this way, solidity and emptiness lose their hard, definite meanings. Every surface, every star, every breath is a ripple in something larger, invisible, and profoundly connected. There is no true separation, only patterns interacting across an ocean of potential. Matter, then, is not made of simple stuff. It's made of structure, rhythm, and resonance, of movement in the dark. The universe is less a machine and more a melody played in the silent language of fields. So when you look at your hand or a falling leaf or the distant shimmer of starlight, what you're truly seeing is the same phenomenon in countless forms. The quiet, endless motion of invisible oceans overlapping through everything. You are quite literally a pattern in motion, a fleeting arrangement of ripples in a cosmic sea, and the very deepest vacuum, the space we once called nothing, is where the whole vibrant spectacle begins. The leap from the idea of particles as tiny spheres to matter, as a mere ripple in a continuous field, was one of the greatest conceptual shifts in physics. Yet this vast, overlapping ocean of quantum fields could not exist as random noise. To build a universe as stable and structured as ours, with predictable forces, consistent light, and coherent atoms, the fields themselves must be governed by deep, invisible rules. This is the realm of symmetry, the quiet, profound architecture that gives the entire cosmos its substance. These fields coexist and interact, but they are interwoven through fundamental constraints known as gauge symmetries. In everyday language, a symmetry means something that stays the same when you change how you look at it, like a perfectly formed snowflake remaining perfect no matter how you rotate it, or a reflection in a mirror being identical to the object. In physics, symmetries are far more powerful. They are nature's rules for how forces and particles must remain consistent as they interact. They are the invisible threads that hold the fields together, ensuring that as they vibrate, they do so in harmony and obey the same laws everywhere in the universe. Every force of nature we experience, electromagnetism, the weak nuclear force, responsible for radioactive decay, and the strong nuclear force, which binds protons and neutrons in the nucleus, arises directly from these gauge symmetries. They are, like the grammar of reality's language, defining precisely how energy and matter are allowed to communicate. When you see light, you are witnessing the electromagnetic field speaking through its symmetry. When an atom's nucleus holds together against the immense electrical repulsion of its protons, it is the strong force field doing the talking, governed by its own strict, beautiful symmetry. The elegance of this structure lies in its consistency. Despite the dazzling variety of particles and forces, everything obeys the same core principles. Different fields are simply different expressions of the same deeper symmetry, like different instruments playing from the same sheet of music. For instance, at extremely high energies, such as those that existed moments after the Big Bang, the electromagnetic force and the weak nuclear force unify into a single cohesive force called the electroweak field. This unification proves that what we perceive as separate forces are merely different facets of the same underlying quantum reality. However, the field concept, for all its power, left a persistent mystery unsolved: mass. Before the mid-20th century, scientists puzzled over why some particles have mass while others, like photons, glide weightlessly through space. If all particles were just ripples in fields, why did some ripples encounter resistance, while others did not? The answer lay in a pervasive, ever-present undercurrent that gives the entire system its weight and substance, the Higgs field. The Higgs field is a kind of universal molasses that fills all of space. It's not a force field that pulls things. Instead, it is an energy field that interacts with particles as they move. As particles travel through this field, they couple with it, and in doing so, they gain inertia, which we interpret as mass. Particles that couple strongly with the Higgs field, such as the top quark, acquire immense mass and are heavy. Others, like electrons, barely interact and remain light. The photon, which carries light, does not interact with the Higgs field at all, which is why it has no mass and can race through the universe at its ultimate speed limit. You might say the Higgs field is what allows the quantum structure to become tangible. It gives the universe its substance, not by adding matter, but by shaping how particles move through its quiet resistance. In 2012, when the Higgs boson, the ripple or quantum excitation of the Higgs field, was finally detected at CERN's Large Hadron Collider, it was a quiet triumph for this entire vision of reality. The discovery confirmed the fundamental structure of the fields themselves. It proved that the invisible interwoven web of the quantum fields was not just mathematical poetry, but a true description of how the universe is built. What's remarkable is how serene this architecture is. Despite its complexity, each field dances in harmony with the others, their interactions governed by simple yet profound equations, unity under chaos, music under noise. Physicists suspect that at even higher energies, such as those that existed just after the Big Bang, all fundamental forces might have been unified, one grand field humming with perfect symmetry. Later, as the universe expanded and cooled, this grand unity broke apart. This process of spontaneous symmetry breaking, the cosmic cooling that fractured unity into diversity, may be the reason we have structure at all. When the universe was young and uniform, everything was perfectly balanced. As it cooled, the fields settled into new, different configurations. That process gave birth to the distinctions we know: matter and radiation, forces and particles, attraction and repulsion. The dizzying variety of the cosmos, from starlight to stone, is a direct consequence of this breaking of an initial, perfect symmetry. It's humbling to realize that every particle in your body is a ripple in this unseen sea. The electrons orbiting the atoms in your cells are tiny disturbances in the electron field. The protons and neutrons in your nucleus are knots in the quark and gluon fields, held together by the strong interaction's elegant geometry. Even the gravity that binds you to the Earth, though not yet fully understood in quantum terms, may one day fit into this same framework, another note in the symphony of fields. The universe is not a collection of individual things, it's a pattern of relationships, a self-sustaining network of vibrations that never stops moving, even in apparent stillness. When you look around and see solidity, you're really seeing stable patterns in this cosmic ocean, like standing waves that persist quietly in time. There's a quiet beauty in how this framework, despite its intimidating name, feels less like machinery and more like art. It doesn't describe a cold, deterministic cosmos, but a living fabric woven from energy, structured by symmetry and sustained by balance. Every particle, every interaction, every glimmer of light follows from that graceful design. And yet, for all its precision, this picture is not the final word. It leaves profound mysteries untouched: dark matter, dark energy, and the quantum nature of gravity. It's as though we've traced one exquisite, beautiful section of the cosmic tapestry, but the edges still disappear into shadow. Perhaps deeper symmetries await discovery, hidden in dimensions we cannot yet perceive. Perhaps the universe, like any great work of art, will always retain a hint of mystery, just enough to keep us looking closer and listening more softly. For now, it's enough to appreciate the profound unity beneath the surface, the music beneath the noise, the fields humming beneath all things, invisible yet ever-present, keeping balance, trading energy, and giving rise to everything from the smallest particle to the brightest galaxy. The hidden architecture of fields is not just a theory of physics, it's a testament to the quiet elegance of nature's design. The deeper we look, the less the universe resembles machinery and the more it resembles harmony. A woven fabric of vibration and balance, serene, eternal, and astonishingly beautiful. Before there were stars, before there was light, before even space and time had definitive meaning, there may have been only a tremor, a whisper in the quantum fabric of nothingness. It is one of the most profound questions that science has ever dared to ask. If energy cannot be created or destroyed, then how did everything begin? How did the entire universe, bursting with light, matter, and motion, emerge from what seems to be absolute emptiness? To begin imagining that, we have to let go of the everyday intuitive meaning of the word nothing. In the language of quantum physics, nothingness is not a flat, silent void. It's more like a restless sea, filled with invisible energy and fleeting fluctuations. Even in a perfect vacuum, the space where all particles have been removed, the quantum fields never truly sleep. They quiver, shift, and exchange energy for the briefest instance of time, creating pairs of virtual particles that appear and vanish again before the universe even notices. This restless state is called quantum vacuum fluctuation, and it may hold the secret to how something came from nothing. At unimaginably small scales, such fluctuations are constant, a cosmic jitter that never entirely settles, and if the early universe was once small enough, far smaller than a proton, far denser than any star, then those fluctuations would not have been side effects, they would have been the main event. It's possible that the Big Bang itself was triggered not by an external cause, but by a quantum fluctuation in the primordial vacuum, magnified into existence by its own energy. In this view, creation wasn't a moment when something violated the laws of physics. It was a moment when the laws themselves allowed a spontaneous transition, a transition from potential to reality. Quantum theory permits such transitions so long as the total balance of energy remains zero. If that sounds paradoxical, imagine a simple scale. On one side sits positive energy, matter, radiation, and motion. On the other side sits negative energy, the gravitational pull that binds everything together. When you add them up, the total energy of the universe may, astonishingly, equal nothing at all. That is the essence of the zero-energy universe hypothesis, that the cosmos could arise spontaneously without violating conservation laws because the sum total of its energy is perfectly balanced. Expanding space creates negative gravitational energy that precisely offsets the positive energy stored in matter and light. It's like an intricate accounting trick at the heart of creation, everything from nothing, yet nothing lost. During the universe's earliest moments, this delicate balance may have been supercharged by an event called cosmic inflation. Inflation is the idea that in the first tiny fraction of a second after the Big Bang, the universe expanded exponentially, faster than light, faster than thought, stretching quantum ripples into vast cosmic structures. The energy driving that rapid expansion likely came from the vacuum itself, a form of immense stored energy associated with a hypothetical field that permeated all space. When that vacuum energy released, when the inflation field decayed, it unleashed an immense flood of particles, radiation, and structure. The universe instantly heated, glowed, and began to evolve into the cosmos we now observe. Every star, every atom, every heartbeat that would ever exist began as a flicker in that burst of expansion. Inflation didn't just make the universe large, it also made it remarkably smooth. Quantum fluctuations amplified to cosmic scale became the seeds of galaxies. The same tiny jitters that once defined the behavior of particles now define the distribution of stars across billions of light years. It's astonishing to realize that the grand architecture of galaxies began as quantum noise, the universe's own fidgeting, magnified across eternity. Galaxies are what happens when the universe can't stop fidgeting. Once inflation ended, the universe continued to expand, but slower. The regions that were ever so slightly denser began to attract more matter through gravity. Over millions of years, this imbalance grew. What started as a difference of 1 part in 100,000 became the first cosmic structures, clusters of gas that would cool, collapse, and ignite as stars. In a way, galaxies are fossils of quantum physics. Their shapes, their distributions, their very existence trace back to random fluctuations, in an otherwise smooth sea of primordial energy. Every spiral arm of stars, every glowing nebula, every planet that would someday circle a sun, all of it can be traced to those original quantum ripples. We have a snapshot of that moment, frozen in the sky, the cosmic microwave background, CMB. It's the faint afterglow of the Big Bang, a wash of ancient light that fills the universe. When we look at it with sensitive instruments, it appears remarkably uniform. But those tiny variations, that faint mottling of brightness, are the fingerprints of those ancient quantum fluctuations. Scientists map these patterns with incredible precision. From them, they can infer the conditions of the early universe, the rate of its expansion, and even the seeds of its future structure. Each faint patch of extra warmth corresponds to a slightly denser region, which would one day become a galaxy or a cluster of galaxies. In those maps, you can almost see the universe's first daydreams, delicate hints of what it would grow into. It's hard not to be amazed by the scale of the transformation. Quantum fluctuations are unimaginably small, a billionth of a meter. Galaxies, by contrast, stretch for hundreds of thousands of light years. Between those extremes lies a bridge built by cosmic expansion and time. The universe took microscopic irregularities and turned them into the vast cosmic web we see today, an interconnected network of filaments and voids stretching across billions of light years. The logic behind it all is simple yet profound. Gravity pulls. It amplifies differences. Where there's a little more matter, gravity draws in even more. Over time, the small becomes large, the faint becomes bright, and the random becomes meaningful. What's even more remarkable is that without those imperfections, nothing would exist. If the early universe had been perfectly smooth, gravity would have had nothing to work with. There would be no clumps to form stars, no stars to forge elements, no planets, no life. Perfection, ironically, would have meant emptiness. The universe needed those flaws, those tiny ripples, to become interesting. Every imperfection was a seed of creation. This gives a poetic twist to our understanding of existence. The cosmos we know and love, with its galaxies, stars, and living beings, owes its existence to quantum uncertainty. The same randomness that seems so capricious in the microscopic world becomes, on a grand scale, the architect of everything. From the smallest tremors came the largest patterns. From the faintest whispers came the loudest symphony. When we think of the Big Bang, it's easy to imagine an explosion happening somewhere in pre-existing space. But that image is misleading. The Big Bang didn't happen in space. It created space. Before it, there was no where or when. Time itself unfolded with the universe. And yet, quantum mechanics allows us to explore even this conceptual edge. Some cosmologists propose that our universe could have emerged from a prior quantum state, a timeless, probabilistic foam where universes constantly flicker into and out of being. It's possible then that our universe is just one bubble in a vast eternal sea of quantum creation. If this is true, then the Big Bang wasn't the beginning of everything, but the beginning of our patch of everything, one verse in a cosmic symphony that has no final note. This perspective leads to a quietly astonishing realization. Existence itself may not require an external cause. The universe might simply be what happens when potential meets probability. The laws of physics, or perhaps the deeper rules that cause those laws, may make existence inevitable, like a song that must be sung once the instrument is tuned. The total energy of the universe might indeed sum to zero, yet that zero is filled with meaning. The positive energy of matter and light is matched by the negative energy of gravity, leaving a net result that is astonishingly nothing. But it is nothing that glows, expands, and dreams. This concept is supported by observations. The universe appears to be remarkably flat, meaning its geometry perfectly balances energy and gravity. The CMB reveals no edge, no preferred direction, no sign of external influence. Everything we see fits a universe that created itself from its own quantum potential, expanding into the balanced, self-contained cosmos we inhabit today. It's almost as if existence is a perfect equation written across the void, where every positive term is mirrored by a negative one, and the total remains unchanged. When you think of it this way, the mystery of creation transforms from why is there something instead of nothing, into how could there not be? If quantum fields can never rest, if even the deepest vacuum still hums with energy, then perhaps the emergence of a universe is not an anomaly, but an inevitability, the natural expression of a restless reality that refuses to stay empty. And yet even that answer leaves us with awe. Because if existence is the ultimate symmetry, then everything we know, every atom, every thought, every heartbeat, is part of that perfect balance. The cosmos may have emerged from nothing, but it did so in a way that conserved everything. No energy was stolen from beyond, no law was broken, no miracle was required. Perhaps existence itself is the miracle, the equilibrium of opposites so profound that it gives rise to stars, to consciousness, to the quiet beauty of wondering why. The universe began as a flicker, and from that flicker it learned how to shine. In the everyday world, barriers are absolute. A solid wall stops a moving ball, a locked door remains firmly shut unless you possess the key, and a table holds a cup with predictable, unyielding certainty. But in the quantum world, the rules are far more forgiving, or perhaps far more mischievous. Down there, at the level of the smallest particles, things sometimes happen that defy our deepest, most comfortable intuitions. Particles sometimes slip through energy barriers they should never be able to cross. They don't crash through, nor do they break the barrier down. They simply appear on the other side, as if the obstacle were only half real. This strange behavior is known as quantum tunneling, and it is one of the most counterintuitive yet absolutely essential phenomena in all of physics. Without it, the sun wouldn't shine, modern electronics wouldn't work, and the universe itself might look fundamentally cold and dark. It is the quiet art of defying the impossible, not through brute force, but through a gentle, persistent trick of probability. To understand tunneling, you must first let go of the classical image of a particle as a small, hard ball. Imagine a tiny ball rolling toward a hill. In the classical world, if the ball doesn't have enough energy to climb over the top, it simply rolls back. There is no middle ground. Either it has enough energy or it doesn't. But in the quantum world, the particle is not a solid object. It is a wave of probability, a spread-out cloud describing where it might be. When that probability wave hits a barrier, the energy hill, part of the wave bounces back, but another part seeps through the obstacle, like a faint echo appearing on the other side. This is not magic or teleportation. It is the fundamental mathematics of waves. The quantum wave doesn't stop neatly at the wall. It fades gradually inside the barrier. And in that fading, there is always a small, finite chance that it continues to exist beyond the boundary. If you waited long enough, you might find the particle has subtly tunneled through. The higher or thicker the energy barrier, the smaller the chance, but critically, the chance is never zero. At the quantum scale, even walls have a soft-hearted, permeable side. It's a wonderful thought, really. Nature allows a little flexibility, a little forgiveness. What seems impossible from one perspective becomes merely improbable from another. And in a universe fundamentally built on probabilities, improbabilities happen all the time, steadily and constantly. One of the most spectacular examples of quantum tunneling takes place invisibly in the hearts of stars. In the core of a star like our Sun, hydrogen nuclei, which are simple protons, are constantly trying to fuse together to form helium. But there is a tremendous problem. Each proton carries a positive electric charge, and like charges repel each other with fierce determination. To get close enough to fuse, they would need to overcome a tremendous energy barrier created by this electrostatic repulsion. The temperatures inside the Sun, though immense, around $15 million deg, are not quite high enough to make that fusion happen by sheer brute force alone. Most protons bounce off before they get close enough, yet fusion happens anyway, billions of times every second, keeping the Sun stable and bright. How? Because of quantum tunneling. The proton's quantum waves overlap, and occasionally, a proton's probability wave leaks through the energy barrier. The particle, in a quantum sense, borrows just enough probability to find itself on the other side of the repulsive force, where the strong nuclear force instantly takes over and binds it with its partner. Without this essential loophole in nature's rules, the gentle willingness of the quantum world to let the impossible happen, the sun would be cold and dark, and life would never have begun. Every ray of sunlight that touches your face is a quiet, continuous testament to quantum tunneling at work, enabling the stars to burn for billions of years. The same principle explains another mysterious process, alpha decay. This is the slow way some heavy, unstable atoms naturally shed particles over time. Inside the nucleus of such an atom, clusters of protons and neutrons, called alpha particles, are trapped by the strong nuclear force. Classically, they do not have enough energy to escape the nuclear boundary, but their quantum wave extends beyond the nucleus, and every so often part of that wave makes it through the barrier. When it does, the alpha particle instantly appears outside, carrying energy with it. It's as if the nucleus occasionally sighs, letting go of a tiny piece of itself through sheer quantum chance. Tunneling isn't confined to the realm of stars and nuclei, it's woven into the technology of everyday life. The modern world runs on semiconductors, the delicate materials that form the heart of computers and smartphones. Inside these materials, electrons must move through tiny, thin barriers that should, by classical logic, stop them cold. Quantum tunneling allows them to flow through specific regions, creating the precise behavior that engineers design into transistors and diodes. The reason you can listen to music, read this sentence, or send a message halfway around the world is that electrons at the smallest scales are unbothered by human definitions of impossible. There's even a specific device, the Scanning Tunneling Microscope, STM, that uses this effect to map the positions of individual atoms. A sharp metal tip hovers just above a surface, and electrons tunnel between the tip and the atoms below. By measuring that tiny current, scientists can map the surface with astonishing precision, revealing not just molecules, but the actual patterns of their quantum states. The device that lets us see the invisible works only because particles can gently slip through walls. When tunneling was first proposed, even seasoned physicists found it difficult to believe. The idea seemed absurd. How could something cross a gap without going over it? But experiments quickly confirmed it. Quantum particles do not obey the binary probabilities that can never quite reach zero. Chaotic, but it is precisely the opposite. Quantum tunneling is not a violation of laws, it's a consequence of them. It happens not in spite of order, but because of it. The universe allows for a little randomness at the smallest scales, and out of that randomness comes stars, chemistry, and life. There's something quietly poetic about this. The same principle that powers our sun also enables our electronics. The same rule that lets light escape from the heart of atoms also lights the modern world. Every tunnel, from the atomic to the astronomical, tells the same story. That possibility is never fully extinguished. It's easy to think of tunneling as strange or abstract, but it reflects something deeply natural. The idea that even boundaries have a hidden texture. In the quantum world, barriers are more like soft membranes than rigid walls. If particles can tunnel through energy barriers, perhaps it's no wonder that stars can burn for billions of years and that life, built from improbable chemistry, can persist against the odds. When you zoom out and think of it this way, tunneling becomes less of a curiosity and more of a quiet act of generosity from the universe. It's nature's way of saying, you may pass even when classical reason says you shouldn't. And it's through this quiet, improbable crossing of invisible walls that the cosmos powers itself. The energy of stars, the birth of elements, the light that reaches us across the void, all of it depends on tunneling. It's a fundamental reminder that sometimes even the smallest chance is enough to keep the universe's fires burning. At the heart of every star, far beneath its glowing surface, there's a quiet miracle happening, one that depends entirely on the strange generosity of quantum physics. Deep in those cores, under pressures and temperatures beyond human imagining, atoms are engaged in a constant struggle between repulsion and attraction. Each atomic nucleus is positively charged, and like all positive charges, they push each other away with fierce determination. By every law of classical physics, they should never come close enough to fuse, and yet somehow they do. This paradox is central to creation itself. Every glimmering point of light in the night sky, every sunrise that warms the earth, every flicker of life that depends on that warmth, all of it exists because of a delicate quantum trick, tunneling. Inside the core of a star like the Sun, hydrogen atoms are squeezed together under crushing pressure. The temperature there reaches around $15 million degrees C, hot enough for the atoms to move at tremendous speeds. Still, their electrical repulsion should keep them apart, creating a massive energy barrier. The kinetic energy they carry simply isn't enough to classically overcome that barrier between them. But in the quantum world, barriers are never absolute. As we've seen, particles are not little solid spheres, they are waves of probability, and those waves can overlap. When two protons, hydrogen nuclei in a star's heart, come close enough for their quantum waves to mingle, there's a tiny chance, a 1 in a billion kind of chance, that they will tunnel through the electrical repulsion barrier and merge. When that happens, they release a flash of energy and form a new, heavier element, helium. The entire process is known as nuclear fusion, and it is the quiet, invisible work that powers the stars. Quantum tunneling, invisible and unstoppable, allows matter to fuse where classical physics says it shouldn't. It's the spark that keeps the universe alight. Each time two protons successfully fuse, a small portion of their combined mass is lost, transformed into energy according to Einstein's famous equation, equal $2. That energy radiates outward, bouncing between countless particles, slowly finally escaping into space as starlight. The glow that reaches your eyes tonight might have begun its journey long before recorded history, born in a quiet quantum event deep within the Sun's heart. If you could somehow stand at the core of a star, not that you'd survive long enough to admire it, you'd see a world of perpetual creation. Particles dart and collide, quantum waves overlap, and in each instant, the improbable becomes inevitable. It's a vast humming sea of light in the making. What's remarkable is not just that this happens, but how perfectly balanced it is. If quantum tunneling were even slightly more likely, stars would burn through their fuel too quickly, flaring out in short-lived bursts. If it was slightly less likely, fusion would rarely happen at all, and the cosmos would be cold and dark. Instead, it sits delicately in between, just enough to light the universe, but slow enough to let it endure for billions of years. This improbable balance is the fundamental reason we have time, warmth, and life. Over those billions of years, fusion does more than produce light. It quietly creates the elements themselves. The universe began with almost nothing but hydrogen and helium, the simplest building blocks. But inside stars, those simple atoms are forged into heavier ones, carbon, oxygen, nitrogen, and beyond. In the most massive stars, fusion continues through layers of elements, stacking one atop another like the rings of an onion until iron forms at the center, the end of the line for fusion's efficiency. When those massive stars finally die, their cores collapse and explode in titanic supernovae, scattering their forged elements across the cosmos. Every atom heavier than hydrogen or helium, including the calcium in your bones, the iron in your blood, and the carbon in your DNA, was once part of a star's heart. Those elements traveled across space for millions or even billions of years before becoming part of planets, oceans, and eventually you. It's humbling to realize that every living thing, every rock, every drop of water is a product of this process, the quiet labor of countless stars transmuting matter through quantum fire. The sun that warms your face today is part of that same story, a continuation of a lineage stretching back to the first stars that ever burned. And yet, for all its grandeur, the process itself depends on something as subtle and uncertain as quantum tunneling, the faint overlap of probability waves inside an atom. From the outside, a star seems fierce, violent, and burning. But inside, its light is born not from violence, but from delicate chance. It's not brute force that powers the cosmos, but a whisper of probability, the universe's gentle willingness to let the impossible happen once in a while. You can think of a star as an enormous, self-sustaining quantum engine. Its heart converts matter into light through processes that depend on both relativity, equal $2, and quantum mechanics tunneling, the two great pillars of modern physics. Without the interplay of both, the star would fail. Relativity explains how much mass becomes energy, while quantum mechanics explains how it happens at all. Each photon that escapes a star carries a story of those laws working in harmony, the smallest scales shaping the grandest outcomes. As that light spreads through the cosmos, it becomes the lifeblood of galaxies, fueling the chemistry of planets and the growth of living things. The warmth you feel on your skin from sunlight is ancient energy, born billions of years ago in an atomic embrace that defied the odds. That same quantum spark continues to flow outward, touching everything it meets, connecting all things in an invisible chain of energy and time. When you look up at the night sky, you're not just seeing distant points of light, you're looking at the ongoing story of quantum mechanics playing out on a cosmic scale. Each star is a living reminder that the rules governing the smallest particles can create the most magnificent structures. The dance of uncertainty at the heart of atoms has expanded to illuminate galaxies. It's a beautiful irony that the universe's greatest certainty, the steady light of the stars, arises from its smallest uncertainty. The trembling of particles, the flicker of quantum probability, becomes the glow that fills the heavens. And perhaps that's the quiet lesson behind it all, that fragility and endurance aren't opposites. The most enduring light in the universe comes from the most delicate process imaginable. From trembling probabilities comes the strength to shine for billions of years. The next time you watch the sunset or trace the path of a star across the night, remember that its light began as a quantum whisper. It tunneled through barriers that should have stopped it, burned for eons in perfect balance, and crossed the cold expanse of space to reach you. You are, in a very real sense, the cooled ash of quantum fire, shaped by the fusion of stars, bound by the same laws, and glowing still with the borrowed light of the cosmos. It's a humbling, comforting realization that the most fundamental process in the universe, the creation of light and life, is powered not by force, but by the subtle, patient probability of quantum chance. If quantum mechanics sounds distant, all about subatomic particles, energy fields, and the birth of stars, it might surprise you to learn that the same strange rules also subtly guide the living world. Life, in its quiet brilliance, hasn't just learned to live with quantum effects, it actively uses them. Plants, animals, and even the cells in your body take advantage of nature's smallest tricks to make existence profoundly efficient and possible. It's as though evolution peeked beneath the curtain of classical physics and thought, this could be exquisitely useful. For much of the 20th century, scientists assumed quantum mechanics belonged only to the microscopic realm, the world of electrons, protons, and photons, not to birds and trees. Living systems seemed too warm, too noisy, and too chaotic to preserve the delicate quantum states required for these subtle effects. After all, quantum coherence often collapses the moment it is disturbed. Yet, over the last few decades, accumulating evidence has shown that life has an uncanny knack for coaxing the improbable into reality, sustaining fragile quantum states just long enough to gain an enormous evolutionary advantage. One of the finest examples of this is hidden in the quiet efficiency of photosynthesis. Every green leaf, every blade of grass, and every patch of algae floating on the ocean's surface relies on an almost miraculous energy transfer process that begins when a photon, a single particle of light, is absorbed by a molecule of chlorophyll. That photon's energy must be delivered with perfect precision and minimal loss to a specific reaction center where it can be stored as chemical energy. In the classical view, the photon's energy would bounce randomly from molecule to molecule, following a slow and highly inefficient path until it found its final destination. But nature has found a far better way, a quantum way. Experiments have revealed that during this energy transfer, the energy doesn't simply choose a single path. Instead, it explores all possible paths at once in a state of quantum coherence. The energy wave ripples through the leaf's complex molecular structure like a symphony of possibilities, sampling every route simultaneously, then instantly and subtly collapsing onto the most efficient one. It's like a traveler trying to find the quickest route through a massive maze. But instead of wandering around aimlessly, The traveler splits into a million versions of themselves, explores every path in parallel, and instantaneously reunites on the best road. That is quantum mechanics in action, and plants do it effortlessly every second of every day. This coherence lasts for only trillionths of a second, yet it's enough to boost the efficiency of photosynthesis far beyond what classical physics predicts. It's nature's way of whispering that the quantum world isn't just strange, it's astonishingly practical and highly optimized. But plants aren't the only masters of quantum art. Some birds, particularly migratory species like the European robin, appear to navigate across entire continents using a quantum effect related to entanglement. For years, scientists wondered how these birds could sense the Earth's faint magnetic field with such staggering precision. They don't carry physical compasses, and the field is far too weak to detect through nerves or muscle alone. The answer seems to lie within their eyes. Inside some birds' retinas are specialized molecules called cryptochromes. When struck by light, these molecules form pairs of electrons whose spins become entangled, linked in such a fundamental way that what happens to one instantly affects the other, even when slightly separated. The subtle alignment of Earth's magnetic field influences the rate at which these entangled spins change, subtly altering the chemical signals the bird's brain receives. In essence, the bird can see the magnetic field not as a color, but as a shifting visual pattern overlaid on its ordinary vision. Imagine flying thousands of kilometers through fog and darkness, guided not by landmarks but by the invisible, quiet hum of the planet itself. That's quantum navigation. Fragile, improbable, yet exquisitely real. The thought of life using entanglement might sound like science fiction, but experiments in controlled environments have supported the idea. The quantum link in cryptochrome molecules seems to persist long enough to influence biological processes, defying the old notion that warm, wet systems can't host such delicacy. Robin, unknowingly, has become a natural quantum experiment in flight. And it's not just plants and birds. Even the enzymes that make chemistry run inside your cells rely on quantum effects to do their jobs efficiently. Enzymes are nature's molecular machines, catalysts that speed up chemical reactions, often by factors of millions or billions. They do this by guiding tiny particles, like electrons or protons, from one molecule to another. But sometimes the energy barriers between those molecules are too wide for the particles to cross by classical means. So what does nature do? It tunnels through. Just as in the quantum tunneling that powers the sun's fusion, particles inside enzymes can penetrate energy barriers they shouldn't be able to cross. Instead of climbing over the wall, they simply appear on the other side, making reactions happen far faster than they otherwise would. This process, known as quantum tunneling, underlies everything from how we metabolize food to how our DNA is repaired. Life, it seems, dances effortlessly along the very edge of the quantum world, tapping into its speed and efficiency. Even processes like smell may have a quantum dimension. Some researchers have suggested that when a scent molecule enters a receptor in your nose, the way it vibrates at the quantum level might help determine how it's recognized, rather than just its shape. The idea remains debated, but it hints at a recurring theme. Wherever life finds efficiency, quantum mechanics might not be far behind. It's worth pausing to consider what this means philosophically. Life has evolved within the quantum universe, shaped by its probabilities and uncertainties. It's not separate from them. Every cell is a tiny, self-sustaining physics experiment, finding stability through chaos and structure through chance. The line between physics and biology blurs, because at the deepest level, they are the same story, energy organizing itself into something that can think, move, and dream. The quantum effects we see in living systems aren't signs of mysticism, but of adaptability. Nature doesn't waste good tricks. When a subtle quantum mechanism works, whether it's the sun fusing hydrogen through tunneling or a leaf capturing photons through coherence, evolution finds a way to use it. The principle is the same. Use the universe's smallest rules to build the biggest wonders. If we could perceive the world at that quantum scale, perhaps life would look less like a collection of separate organisms and more like a vast field of interactions, an orchestra of energy and probability humming in exquisite harmony. Every photon absorbed, every molecule formed, every heartbeat that follows is part of that same rhythm. The next time you see sunlight filtering through leaves or a bird tracing invisible lines across the sky, remember that these are not just poetic images. They are acts of physics, life, tapping into the quantum engine of the universe. The line between living and fundamentals is thinner than we think. From the trembling of electrons in chlorophyll to the tunneling protons in your cells, life doesn't merely exist in the quantum world, it is of it. Each breath, each moment is sustained by processes that blur the line between certainty and possibility. Life hums in harmony with the quantum scale, a soft melody that began billions of years ago and still echoes through every leaf, every wing, and every pulse of your heart. The subtle dance of quantum mechanics, which governs the quiet birth of starlight and the hidden structure of atoms, find that the strange rules of the quantum world have evolved to use quantum effects as a fundamental survival tool. This turns the concept of a biological compass from a simple neurological process into a phenomenon rooted in the deepest laws of physics. For years, scientists wondered with quiet fascination how birds, especially long-distance migratory species like the European robin, could navigate across entire continents and oceans with such staggering precision. They don't carry physical magnetized compasses, and the Earth's magnetic field, though vast, is incredibly weak, far too faint to be detected through nerves or muscle in a simple, classical way. A traditional compass needle is a large, macroscopic object. Detecting the magnetic field requires a sensor that is subtle enough to respond to the field's minimal force without being overwhelmed by the constant noise and warmth of the living body. The key to this incredible, delicate navigational ability appears to lie in the eyes of these birds. Specifically, within the retina, scientists have identified specialized molecules called cryptochromes. These molecules are light-sensitive proteins, and when struck by the extremely low energy of blue light, they initiate a quiet chemical reaction that involves a pair of electrons. When the cryptochrome molecule absorbs a photon, it briefly creates a pair of electrons whose spins become entangled. Quantum entanglement is perhaps the most famous and baffling phenomenon in physics, often described as spooky action at a distance. It means that these two electrons are linked in such a fundamental way that what happens to the spin of one instantaneously affects the spin of the other, regardless of the physical distance between them. In the bird's eye, these entangled spins form a quantum link. This quantum link is critically sensitive to external magnetic fields. The direction and strength of the Earth's magnetic field directly influences the rate at which these entangled spins transition and rearrange themselves. This subtle influence, in turn, subtly alters the final chemical products of the cryptochrome molecule. Instead of the bird needing a large, clunky piece of iron to sense the field, it uses the subtle change in a chemical reaction powered by these quantum-linked electrons. The bird does not consciously interpret these quantum changes as north or south in the human sense. Instead, the resulting chemical signal is sent to the brain, likely creating a form of visual pattern or an intensity overlay on its ordinary vision. Imagine flying thousands of kilometers through fog and darkness, guided not by visible landmarks, but by a shifting, subtle pattern of light intensity or contrast that corresponds directly to the invisible quiet hum of the planet itself. That is the astonishing concept of the quantum navigator. This entire process is exquisitely delicate. Quantum coherence, the state where particles exist in multiple possibilities simultaneously like these entangled spins, is notoriously fragile. It usually collapses immediately when interacting with a warm, noisy environment. Yet, life, in its strange genius, has found a way to protect and sustain this quantum state, just long enough to extract the necessary information. The cryptochrome protein acts as a tiny molecular quantum laboratory, shielding the entangled electrons from the surrounding heat and chaos for a few millionths of a second, a fleeting duration that is nevertheless long enough to measure the magnetic field's subtle influence. The thought of living systems using entanglement might sound like science fiction, but experiments in controlled environments have increasingly supported the idea. The quantum link in cryptochrome molecules seems to persist just long enough to influence the rate of biological processes, defying the notion that warm, wet systems cannot host such quantum delicacy. The robin, without ever knowing the name Heisenberg or Schrödinger, has become a natural quantum experiment in perpetual silent flight. This discovery has profound implications for how we define the boundary between the living and the non-living. It suggests that evolution did not stop at classical Newtonian mechanics, but pushed right up to the edge of the quantum world, exploiting its deepest rules for survival advantage. Where classical physics would predict random error and inefficiency in the bird's navigation, quantum mechanics predicts and explains the observed precision and speed. The bird uses the probabilistic nature of the quantum world to achieve a highly reliable, non-probabilistic result. And it's not just in avian navigation. As we explored, the same quantum principles of coherence and tunneling are essential to the speed and efficiency of photosynthesis and to the precision of enzymatic reactions that repair your DNA and metabolize food. Life is fundamentally leveraging the universe's inherent uncertainty to achieve stability. The complexity of the magnetic field itself is also part of this quantum dance. The field varies subtly across the globe, providing birds with not just a directional compass, but likely also a latitudinal map, information about their distance from the equator. The robin's ability to detect not only the direction of the field, but also its subtle inclination, the angle at which the magnetic field lines dip into the Earth, is crucial for migration. All this information is captured by the quantum spin of those electron pairs in the eye. Imagine the universe communicating directly with the bird's chemistry, providing an invisible, built-in map. This phenomenon requires a fundamental rethinking of biological efficiency. The quantum effects we see in living systems are not merely scientific curiosities, they are a deep, quiet expression of nature's adaptability. The system is optimized to capture the maximum information from the weakest possible signal. It's the ultimate example of doing more with less, turning a noisy signal into a clear, usable direction. The next time you see a bird tracing invisible lines across the sky during its seasonal migration, remember that these are not just poetic images, they are acts of quantum physics. The bird is tapping into the quantum engine of the universe, sustained by processes that blur the line between certainty and possibility. The line between living and fundamentals is thinner than we think. From the trembling of electrons in chlorophyll to the quantum-entangled spins in a robin's eye, life doesn't merely exist in the quantum world, it is of it. Each flight path, each moment of sensing direction, is sustained by processes that confirm life hums in harmony with the quantum scale, a soft, invisible melody that still echoes through every wing and every beat of your own heart. The quantum navigator, flying quietly through the vast, dark night, is a perfect, enduring reminder that the smallest rules of reality create the grandest, most beautiful wonders. If quantum mechanics governs everything from atoms to galaxies, if the very foundation of reality is built upon a shimmering sea of probability, then why doesn't the world around us look quantum? Why don't we see tables in two places at once, or feel our bodies dissolve into a hazy cloud of uncertainty? Why do things seem so solid, so certain, so predictable, when at their core everything is built from probability and jittering motion? The answer lies in one of the most subtle and elegant ideas in modern physics, a continuous, unavoidable process called decoherence. Decoherence is the quiet bridge between the strange, unseen quantum world and the familiar, definite classical world. It is the reason why we can live in a realm of definite shapes and clear outcomes, even though everything underneath is a blur of potential. It's not that quantum mechanics stops applying at larger scales. It never stops. Instead, as systems grow bigger, they become almost instantly entangled with their surroundings, with the air molecules, the heat, the light, and the myriad of other particles that make up their environment. This entanglement happens in such a way that the delicate quantum behavior we associate with tiny particles, superposition, being in two states at once, interference and entanglement, becomes effectively invisible or washed out. In the pure quantum world, a particle can exist in many possible states at once. Its wave function describes a continuous cloud of probabilities. But the moment the particle interacts with its environment, with air molecules, stray photons of light, or a whisper of heat, those possibilities begin to collapse into one single outcome. The quantum wave doesn't vanish in a puff of mystery. It simply spreads its coherence among countless other particles until the original unique quantum pattern is too complex to trace or measure. Think of a single violin playing a pure, clear note in a quiet room. You can hear every subtle vibration, every delicate overtone of the instrument. But if that same violin starts playing in the middle of a torrential thunderstorm, the notes are still technically there. They're just completely drowned out in the roar of the wind and rain. The melody hasn't disappeared. It's been lost in the noise. That is the perfect analogy for decoherence. Quantum systems are like those fragile notes, clear and distinct when isolated, but quickly overwhelmed by the chaotic, noisy orchestra of the environment. In a sense, every measurement we make is just another form of entanglement that leads to decoherence. When you observe a particle, you are not forcing it to make a choice. You are simply linking it to a much larger, messy web of interactions. The measuring device, the air around it, the photons bouncing off it, all become part of one enormous interconnected system. The coherence that once defined the particle's quantum state becomes smeared out across so many degrees of freedom that it no longer behaves in a measurable quantum way. What remains is the predictable, single-outcome classical world that we recognize. This transition isn't sudden. There is no precise moment when reality decides to become classical. Instead, it's gradual and completely inevitable. It's a continuous, rapid exchange between the pure, delicate quantum domain and the noisy, entangled complexity of everything else. The more particles involved, the faster the coherence fades. A single electron can remain quantum for ages, a tiny dust grain for nanoseconds, and a macroscopic object, like a cat, for an even smaller, unimaginable duration. To make this less abstract, imagine ripples on a perfectly calm pond. Each ripple represents a possible state, overlapping and interfering to create a beautiful, complex pattern. But then it starts to rain. Each new raindrop adds new ripples, new disturbances, until the original coherent pattern disappears into chaos. The pond hasn't stopped being made of water, it's just too disturbed for the original delicate waves to be seen. Likewise, the universe hasn't stopped being quantum, it's just too noisy at large scales for us to see the original fundamental waves anymore. This constant blurring of quantum states is what allows the world to appear stable. Without decoherence, everything would remain uncertain, smeared across infinite possibilities, and boundaries would never settle. But thanks to interactions with the environment, those possibilities are constantly and passively being narrowed down, not through some magical collapse, but through the simple, statistical washing out of interference. Macroscopic calm is built from microscopic confusion. And yet, for all its serenity, decoherence is not destruction. The quantum information isn't actually gone, it's just dispersed into the environment. In theory, if you could perfectly track every particle in the environment, every photon, every vibration, every stray interaction, you could potentially reconstruct the original quantum state. In practice, however, that is utterly impossible. The universe's information web is too tangled for any observer to unwind. What we call reality is simply a practical version of quantum mechanics, the one that emerges when all the fine quantum details are blurred and averaged together. This might sound abstract, but it's at the core of some of today's most exciting technologies, especially quantum computing. Quantum computers rely entirely on maintaining coherence, keeping their quantum bits of information, or qubits, in delicate superpositions of states for as long as possible. These superpositions allow quantum computers to explore many possibilities at once, solving certain complex problems far faster than any classical machine could. But the challenge is monumental. Every stray vibration, every whisper of heat, every cosmic ray that touches a qubit threatens to destroy its coherence. Engineers go to extraordinary lengths to protect quantum systems from decoherence, cooling them to near absolute zero and shielding them from electromagnetic noise with exquisite precision. The task is like trying to keep a fragile soap bubble intact inside a hurricane. And yet, this struggle has taught us something profound. Decoherence isn't a flaw in quantum mechanics, it's the very reason we can experience a stable world. If coherence lasted forever, the boundaries between possibilities would never settle, and the now would never arrive. In a sense, decoherence gives us the present moment. It allows quantum potential to crystallize into classical, understandable experience. The more you think about it, the more it feels like the universe is performing an endless act of translation. At the smallest scales, it speaks in probabilities and waves. At best, it speaks in certainties and definite forms. Every interaction, every exchange of energy, every observation is part of that translation, a quiet, continuous conversation between quantum truth and human perception. We tend to imagine the quantum and classical worlds as separate layers of reality, but they are not. They are the same at different levels of resolution. Quantum mechanics is the raw, vibrating fabric. Classical physics is the clear, beautiful tapestry we see when we step back far enough. It's the same universe, just viewed through different lenses. This idea has a quiet beauty. The predictability of our world, the solidity of a table, the reliability of gravity, the comfort of cause and effect, all emerge from a foundation that is anything but predictable. Underneath the calm surface of the everyday world lies a sea of fluctuations, constantly jostling, entangling, and decohering. The fact that we don't see that chaos directly is what allows us to exist within it. So the next time you reach out to touch something solid, remember that what feels certain is fundamentally built from uncertainty. Every object, every atom, every moment of experience is the product of decoherence, the quiet, necessary averaging out of quantum strangeness into classical order. It's easy to think of this as a loss, as though the world has been tamed and its wonder hidden beneath the ordinary. But really, it's an act of deep cosmic balance. The universe has found a way to let chaos cause stability, to let uncertainty give birth to the continuous experience of life. Macroscopic calm is built from microscopic confusion, and in that calm we find the necessary space to live, to think, and to quietly wonder where all the remaining strangeness might still be hiding, just beyond the quiet reach of our everyday senses. The boundary between our predictable lives and the shimmering quantum foundation is not a wall, but a soft, continuously moving bridge to certainty. Whenever a scientific discovery captures the public imagination, myths and persistent misconceptions are never far behind. The idea of quantum energy, those endless ripples in empty space, the constant invisible hum that permeates all of existence, has inspired not just physicists but also dreamers, inventors, and the occasional conspiracy theorist. After all, if the quantum vacuum of space is truly brimming with an immense limitless energy, surely that means boundless power waiting to be tapped. The thought is intoxicating, an infinite source of clean energy, drawn literally from nothingness, capable of fueling entire cities, curing scarcity, and freeing humanity from its dependence on finite resources. It sounds poetic, noble, and unfortunately too good to be true. The misunderstanding often begins with a kernel of real science. As we've explored, the quantum vacuum isn't empty. It teems with zero-point energy, a ceaseless, fundamental background hum that can never be switched off. Measurements and delicate experiments confirm its presence in subtle ways, through effects like the Casimir force and the very stability of atoms. So it's no surprise that the human imagination leaps from there to the notion of harnessing that energy, of dipping a metaphorical cup into the infinite sea of the vacuum. If energy is everywhere, why can't we simply use it? The simple, unsatisfying answer is that nature does not allow it. Quantum mechanics, while granting us a restless, vibrant vacuum, also enforces balance with ruthless precision. The zero-point energy of space is a kind of baseline, the lowest possible level of energy that the universe permits. You can't build a machine that extracts work from it for the same fundamental reason that you can't build a water wheel that turns into a perfectly calm pond. There is no net flow to harness, no difference, no gradient, and without a difference in energy, there is nothing to drive motion or perform useful work. In physics, this rule is enshrined in the law of conservation of energy, one of the most reliable and absolute principles ever discovered. Energy can neither be created nor destroyed. It can only change form, flowing from a high-energy state to a low-energy state. The dream of infinite, free power drawn from the vacuum would require fundamentally breaking this law. It would mean drawing more energy out than was put in, getting something for nothing. And the universe, elegant though it is, does not give out freebies. To imagine why, think of zero-point energy as the ground floor of reality's building. It's the lowest possible level. You can only extract useful work by moving downhill from a higher level to a lower one, like water flowing through a turbine. But zero-point energy is the basement, the bottom of the cosmic well. You can't dig beneath it. You can't go lower. Every process we know of, every engine, every battery, every biological reaction depends on differences between high and low energy states, hot and cold, charged and uncharged, high pressure and low pressure. The quantum vacuum, for all its shimmering, vibrant beauty, doesn't have that crucial contrast. It's perfectly uniformly balanced, and that perfect balance is precisely why everything else can exist upon it. Still, the idea of tapping the void persists, and perhaps it always will. There's a deep romance in the notion of hidden limitless energy, an echo of humanity's eternal wish to transcend limitation. This dream has appeared in countless guises over the centuries. Alchemists' attempts to create the philosopher's stone, speculative plans for perpetual motion machines, and mysterious etheric force generators. Each generation rediscovers the dream, dresses it in the language of its time, and hopes that perhaps this time the laws will bend. Yet these laws are what give the universe its coherence and its beauty. Without the law of conservation, without the quiet, rigid limits on energy flow, there would be chaos. If energy could simply appear from nowhere, the delicate balances that make stars shine, atoms stable, and physics itself intelligible would instantly collapse. Physics would lose its poetry because everything would become arbitrary. The constancy of natural laws, those quiet boundaries around possibility, are what make the universe understandable and beautiful. That's not to say humanity hasn't tapped extraordinary energy sources before. The sun itself operates on quantum principles, nuclear fusion, made possible by the strange dance of tunneling particles and quantum probability. It converts matter into light with breathtaking efficiency, following Einstein's sequel Tom $2. But even that colossal process is constrained by physics. It follows the rules precisely, wasting nothing and creating balance where chaos might have been. Quantum energy isn't infinite power waiting to be unleashed. It's the steady, quiet hum that keeps the cosmos in harmony. Some modern discussions of zero-point energy in popular culture often blur this crucial line, using the phrase as a synonym for a limitless energy source or some kind of mystical force. You'll find it referenced in speculative articles and fictional stories about hidden technologies. It's a captivating idea, how could it not be? But it's not what quantum physics describes. The zero-point energy of space is a fundamental property of fields themselves, not a resource to be mined. It's part of the essential structure, not a prize waiting to be collected. Its implications, when they first encountered the potential immensity of vacuum energy in their equations, startled even scientists. Calculations suggested that if one could somehow release even a small fraction of it, the amount would be staggering. But there's the trick. It cannot be released. It's not stored energy. It's intrinsic energy. It's not potential power waiting to be used. It is the absolute baseline upon which all usable power depends. In a way, it's comforting that we can't exploit it. The vacuum's untouchable energy means the universe remains stable. If we could drain it, we might unravel existence itself. The same hum that seems like wasted potential is what holds everything in place. When you think about it like that, the dream of infinite extraction feels less like a promise and more like a misunderstanding of a deeper, quieter beauty. The laws of physics don't deny us wonder, they create it. They are the reason why the world can be understood, why energy flows predictably, and why matter coheres. If you hold a glass of water and let it sit on a table, gravity pulls it down, and the table pushes back with equal force. Nothing happens because the forces are balanced. The vacuum's energy is like that, a perfect equilibrium. To get useful work, you'd have to unbalance it. But the moment you try, the universe pushes back. Every attempt to tilt the scales only proves how finely tuned they already are. There's a quiet dignity in those constraints. They tell us that, even in a universe bursting with energy, not all of it is ours to command. The boundaries of possibility are not obstacles, they are the architecture of existence. They make life possible, and they give profound meaning to effort and ingenuity. So while the idea of limitless, free quantum power is appealing, it's the limits themselves that make the real story extraordinary. We can admire the hum of zero-point energy, feel awe at its omnipresent nature, and still respect the cosmic balance that keeps it gently beyond our reach. In the end, that's perhaps the most beautiful lesson quantum physics offers. That wonder doesn't depend on fantasy. The truth is already strange enough, vast enough, and miraculous enough. We don't need to break the rules to feel amazed by the world. Believable. And it's in that believability that its quiet, enduring beauty truly lies. Reality's constraints make its beauty believable. The energy of the void is not a prize, it's the foundation. If the universe could take a deep breath, it would never exhale. Instead, it would keep expanding forever, stretching the fabric of space itself wider and wider. That is literally what the universe is doing now. Every distant galaxy is moving away from every other, and the farther it is, the faster it recedes. What's stranger still is that this expansion isn't slowing down with time, it's speeding up. Space isn't just growing, it's accelerating outward, as if something invisible were gently pressing the cosmic gas pedal. That invisible something is what scientists call dark energy, an unseen, pervasive pressure that permeates the cosmos, driving everything apart. It doesn't shine, it doesn't clump together with matter. Still, it rules the universe. Roughly 70% of all the energy in existence is dark energy, and though we can measure its immense effects on the grandest scale, its true nature remains one of the greatest and most profound mysteries in science. To understand where dark energy might come from, we need to return once more to the concept of the quantum vacuum, that restless sea of invisible energy we've already met. Even in absolute emptiness, quantum fields are never truly still. They flicker, shift, and hum with zero-point energy. It's tempting to think that this endless background activity could explain the universe's acceleration, that the vacuum's own intrinsic energy is what pushes space to expand. This idea isn't new. In fact, a concept strikingly similar to dark energy first appeared in the early 20th century in the equations of Albert Einstein himself. When Einstein formulated his general theory of relativity, the description of how gravity bends and shapes space, he found that the universe should naturally be either expanding or contracting. But at the time, astronomers believed the cosmos was static, unchanging. To accommodate this mistaken belief, Einstein added a term to his equations, the cosmological constant, lambda. This constant acted like a built-in pressure of space itself, a kind of cosmic anti-gravity that could theoretically hold the universe in perfect static balance. A few years later, Edwin Hubble's observations revealed that the universe was expanding after all, and Einstein reportedly called his cosmological constant the greatest blunder of his career. Yet, decades later, when scientists discovered that the expansion of the universe was unexpectedly accelerating, rather than slowing down due to gravity, Einstein's so-called blunder suddenly looked prophetic. The cosmological constant was reborn, this time as a way to describe dark energy. In modern physics, the cosmological constant is often interpreted as the energy of empty space, the vacuum energy predicted by quantum field theory. Every quantum field, even when stripped of all particles, has a residual, zero-point energy that cannot be removed. If you could add up all those tiny zero-point contributions from every field in the universe, you'd expect a truly colossal vacuum energy density. One so enormous it would have blown the universe apart instantly, preventing any stars or galaxies from ever forming. But when physicists actually compare those theoretical predictions to what we observe, there's a staggering mismatch. The numbers differ by a factor of roughly $10.120, a 1 followed by 120 zeros. This is often described as the most embarrassing discrepancy in all science. Somehow, the real vacuum energy is incredibly small, yet not zero, just small enough to let the universe expand slowly, gently, and gracefully, instead of tearing itself apart in an instant. It's as if the cosmos has tuned itself with exquisite precision, balancing on the edge between stillness and explosion. You might picture it like a calm ocean that, despite being vast and deep, only ripples slightly at the surface. Beneath that stillness, unimaginable energy swirls unseen. Every cubic centimeter of space, even in the void between galaxies, contains this hidden hum, a faint residue of quantum activity that quietly shapes the destiny of everything. As space expands, it doesn't dilute that energy. Instead, vacuum energy remains constant per unit volume. So, as the universe grows larger, there is simply more space for that energy to fill, and the total amount of dark energy in the cosmos increases. The result is a feedback loop. More space means more dark energy, and more dark energy means faster expansion. It's a gentle, unstoppable acceleration that stretches galaxies ever farther apart. Eventually, if this continues indefinitely, distant galaxies will vanish from view, slipping beyond the reach of light itself. The night sky will grow emptier over trillions of years, until only the nearest galactic neighbors remain visible. Future observers, if there are any, might never know that other galaxies ever existed. The expanding universe will quietly erase its own history. That may sound melancholic, but there's a quiet beauty in it too. The same vacuum energy that drives galaxies apart is also the reason the cosmos remains dynamic and alive. Without it, gravity might have pulled everything back together long ago in a big crunch. Instead, space itself stretches, powered by its own hidden energy, a quiet pulse woven into the fabric of existence. In a sense, the universe is both growing and resting at once. The galaxies drift apart, but within them, stars are born, planets form, and life unfolds. The expansion doesn't disturb local structures, it only stretches the space between them. From our small vantage point, the cosmos feels still, yet, on a grand scale, it's a living, breathing entity. Scientists continue to seek the true nature of dark energy. It might be a true cosmological constant, a fixed property of space itself, as Einstein hypothesized, or it could be something dynamic, an evolving field that changes over time, a concept called quintessence. Some theories even suggest that dark energy could one day weaken, or conversely grow so strong that it rips apart galaxies, stars, and even atoms in a big rip. For now, the quiet evidence points toward constancy, a steady cosmic hum that has been present since the beginning. It's humbling to realize that what we call nothing may be the most powerful something of all. The vacuum, once dismissed as empty, has turned out to be a creative force, birthing particles, influencing gravity, and shaping the universe's ultimate fate. It's as if reality itself rests on an invisible ocean of energy, endlessly calm, yet infinitely deep. Perhaps, in a poetic sense, dark energy is the universe's way of maintaining balance. Stars burn out, galaxies fade, but space itself carries on, quietly expanding, endlessly renewing. It's not an explosion, but a slow breath, an eternal unfolding that requires no fuel and no external direction. When you look up at the night sky, every pinpoint of starlight exists against that expanding backdrop. The galaxies are not just drifting through space, the space between them is growing. And though we can't see the force behind it, we can feel its echo in the patterns of cosmic light, in the faint afterglow of the Big Bang, and in the very structure of the universe itself. In the end, dark energy reminds us that even the emptiest places are not truly empty. Space is not a void, but a medium, a silent fabric that hums with hidden energy. The same quantum fields that once gave rise to particles and light now shape the grandest architecture of the cosmos. The universe doesn't expand into anything, it expands within itself, carried outward by the invisible tide of its own being. Space itself stretches, powered by its own hidden energy. And in that slow, ceaseless motion, the cosmos keeps time with a rhythm older than stars, softer than silence, and deeper than imagination. It is the ultimate great accelerator, a quiet force defining the shape of tomorrow. After wandering through the strange and shimmering world of quantum energy, it's easy to feel as though you've gently stepped out of a long dream. Everything we once thought was solid has subtly dissolved into vibrations and fields. Everything has become a fluid language of probability. And yet, what emerges from that strangeness is not confusion, but a quiet harmony. The deeper we look into the quantum world, the more we find coherence beneath the chaos, a profound quiet order pulsing through the smallest scales of reality, linking every atom, every photon, and every star. Quantum energy began its story humbly with Max Planck, a dedicated scientist trying to fix a simple problem about how things glow when heated. He wanted mathematics to behave. Instead, he uncovered a new, deep truth about the universe. Energy doesn't flow continuously like water. It comes in packets, tiny quanta, discrete steps in nature's otherwise seamless dance. It was as if the universe, when playing its music, could only strike specific, fixed notes, never slide between them. That single idea, that energy comes in quanta, was the seed from which all of modern physics grew. Einstein turned that seed into light itself, showing that photons were not just waves, but particles, each one a quantum carrying the precise currency of the universe across space. Bohr followed, showing that atoms are not miniature solar systems, but musical instruments, they're electrons, leaping between exact harmonic energy levels. Schrödinger gave the world a new image, matter as melody, probability as poetry, where particles became waves and waves became possibility. And Heisenberg reminded us that certainty itself was an illusion, that the more precisely we try to measure one thing, the less we can know about another. This uncertainty is not a flaw in the design, it is the design. It is what allows the universe to exist in constant motion rather than frozen stillness. Without it, particles would freeze into perfect, silent order, and no change, no life could ever occur. Reality's restlessness is not chaos, but creativity. At the foundation of all this is the concept of fields, invisible sheets of energy that fill all of space. Everything we see, from light to matter to heat, is a ripple in one of these fields. You are made of ripples in the electron field, held together by ripples in the gluon field, warmed by ripples in the photon field. Space isn't an empty container, it's a living ocean of interaction. And within that ocean, energy never disappears, it only changes form. That is the immutable law of conservation, one of the simplest and most profound truths in science. No matter what happens, a star collapsing, a leaf growing, a thought forming in the human brain, the total energy of the universe remains constant. It can stretch, shift, radiate, or transform, but it can never be lost. Even when matter seems to vanish, as in the annihilation of particles, its energy instantly reappears in another form. The universe keeps perfect books. In this light, existence begins to look like a great circulation, a ceaseless exchange between forms of energy. The photons streaming from distant galaxies were once locked inside atoms forged in stars. Those atoms were built from energy released in the early universe. That energy, in turn, emerged from quantum fluctuations in the void, and some of it, after billions of years of cosmic recycling, now powers the cells in your body. You are quite literally made of ancient light, energy slowed, organized, and condensed into thought. It's a humbling idea, and a beautiful one too. You're powered by the same cosmic jitters that light the stars. The warmth in your skin and the glow of the sun both come from the same fundamental quanta, excited in different ways. Every breath, every heartbeat, every spark of awareness is just energy changing its costume, moving from one form of existence to another. Quantum physics shows that beneath every calm surface lies motion, jittering, flickering, vibrating. The vacuum isn't truly empty. At every point in space, quantum fields are alive with zero-point energy, constantly shifting between potential and presence, even though nothing is busy. And it is from this restlessness that order arises. On the cosmic scale, that same quantum hum may be what inflated the universe at its birth, stretching space and time themselves. Tiny fluctuations magnified by cosmic expansion became galaxies, stars, and the atoms in your body. The infinite quiet of the early vacuum became the chorus of existence. From nothing came everything, not through miracle but through balance, positive and negative energy, matter and gravity, perfectly countered so that the sum remains zero. It's a breathtaking symmetry. Every motion in the universe is part of this balancing act. Starlight is balanced by the pull of gravity. The cosmos' expansion is offset by its invisible dark energy. On every scale, energy flows like a tide, never gained, never lost, always transformed. The result is a reality that sustains itself, powered by its own harmony. The more we study quantum energy, the clearer it becomes that we live not in a world made of things, but in a world made of relationships, fields interacting with fields, waves overlapping, probabilities blending. The solidity of a table, the sharpness of light, the persistence of memory, all are manifestations of patterns, not particles. Matter is what happens when energy dances in formation, and what a dance it is. From the smallest particle to the largest galaxy, the universe moves in rhythm with itself. Electrons leap between energy levels, emitting photons that race through space, strike another atom, and set off the next event. Stars fuse hydrogen into helium, releasing light that travels for billions of years to fall upon a planet that uses that same light to grow forests and fuel life. Even thought, that flicker of consciousness, is electrical energy rearranging itself in the quantum web of your neurons. The entire cosmos is one vast interconnected network of exchange. There is no stillness anywhere, not truly. Even at absolute zero, the lowest possible temperature, quantum energy continues to hum softly beneath the silence. Reality never sleeps. Perhaps that's why we find such peace in contemplating it. The universe's order doesn't arise from control but from constant movement. It's a kind of balance that includes uncertainty, a stability born of impermanence. We don't need to understand every equation to feel the wonder of that. It's enough to know that even the quietest moment, even the stillest night, is alive with hidden motion. The same invisible energy that lights the stars hums softly within you. The same quantum fields that shaped galaxies ripple through your being. You are part of the pattern, a fleeting yet eternal arrangement of the universe's own energy, experiencing itself for a little while as human. It's comforting to realize that in a universe ruled by uncertainty, conservation offers a quiet promise. Nothing is ever truly lost. The energy that fuels your body was once starlight. The atoms that build you were once plasma drifting in the newborn cosmos. When your energy returns to the world, it will take new forms, perhaps as heat, as light, as growth in something else. In the great exchange of existence, nothing is wasted and nothing truly ends. Perhaps that's what makes quantum energy so calming to contemplate. It doesn't suggest chaos or randomness, but rather an endless continuity. Even when things dissolve, they persist in new patterns. Even when silence falls, motion continues underneath. The universe never truly stops moving, it only softens its voice. And now, as our journey draws to its quiet end, there is no grand finale waiting, just the same calm hum that began it all, the background tone of existence, still vibrating, still alive. From Planck's first spark to the cosmic whisper of empty space, everything follows the same law. Energy flows, transforms, and endures. You don't need to hold every detail of the science in your mind to feel its truth. You can simply let the idea settle like light filtering through water. You can rest in the knowledge that beneath the stillness of your room, beneath the stillness of your thoughts, the entire universe is gently moving, keeping balance. The same invisible energy that lights the stars hums softly within you. The same quantum fields that shaped galaxies ripple through your being. You are part of the pattern, a fleeting yet eternal arrangement of the universe's own energy, experiencing itself. And as you drift towards sleep, you might take comfort in this, that the cosmos, vast and unending, is at peace with its motion. Its energy hums quietly, changing shape but never ceasing. The night around you is not empty. It's alive, full of gentle vibrations too small to see, too quiet to hear. The universe never truly stops moving, it only softens its voice, and now, in that softening, you can let the silence complete the thought.